Good morning. I'll be quick, I promise. Welcome everyone to day 3 of XDC. Thank you all for coming. Thank you. I hope you all enjoyed yesterday's. We haven't arranged more jackhammering for you this morning, but we'll work on it. I did have one kind of request. We had 4 young men who were clearly making a TikTok video or something, who got in on a tailgate. So if you see 4 young men, one of them with a camera, one of them wearing a referee shirt, don't let them in, okay? That was the whistle and the hullabaloo we had in the hallway yesterday. And that's all I have, and welcome and enjoy the day.
Yeah, just a few usual reminders. Let's keep all of that, useful information. So you probably already know the Twitter and the Matrix channels if you are not there. Same people to reach out today as well. That you probably know. So far, so good with code of conduct. And that's the important part. Please upload your slides. So if you have presented anything during this conference, make sure that you go to Indico, log in, find your submission, and click that crayon button next to presentation materials. Workshop. So there's a second workshop going on, I believe, right now. We're starting very soon. That's the HDR one. So it should be in Schulze Hall 127. So if you want to join that, there's that. There's also a link that was shared in the Matrix by Harry. So if you want to participate remotely, use that. And lightning talks, demos. So if you had a workshop before, or if there's something you want to talk, please submit a lightning talk proposal. And the deadline for that is 3 p.m. today. That we already know. And the shout outs to sponsors. So CodeWeavers, the platinum sponsor and organizer, ARM, AMD, NVIDIA, Google, and Microsoft, all of which are gold sponsor. Silver sponsors, Collabora, the Linux Foundation, FEX-Emu, Igalia, and our bronze sponsor, Kronos Group. So all of those people make this thing happen, and they basically pay for you being here. That's it.
Okay, hi everyone. I will talk today about explicit sync, or rather, not really explicit sync, but disabling implicit sync. So sync here, like synchronization, is when we start are trying to synchronize GPU work with other GPU work. Like, hey, you're submitting something for rendering, and then you want to make sure that, hey, the rendering actually finished before you start to display the thing. And you can do that explicitly. Hey, we have a fence or a semaphore or whatever your API has for specifying that dependency. Or you can do implicit, which is kind of provides a sort of GPU side locking on the buffers that you touch. And I'll do a short intro on like roughly how this works in the kernel. So like the kernel has a DMA fence object that signals the completion of some work, and it can be waited upon, it can be signaled. It has a ton of helper things like callbacks. You just can't reset it, like it's a one-shot thing. And that's how a lot of these dependencies are tracked in the kernel, actually both for implicit and explicit synchronization. And then in the user space, there's some API around this. Like we have a bunch of containers that are user space accessible. Like there's sync objects, which is a container of 0 or 1 DMA events, which can be replaced or reset. So like, hey, when you submit some work, like in a submission, you can say, hey, I have an out sync object, and then a driver may just put a DMA fence in there that can be waited on later. And there's a sync FDR sync file that basically is a file that points to a DMA fence, and it always has a DMA fence that's active. So you can't just have it empty and never signal. And then how does implicit sync work? Well, every buffer has a DMA, every DMA buff has a DMA reservation, and it contains up to 1 exclusive fence and many shared fences. And then like on submit, the user space driver passes a list of referenced buffers, and then the kernel driver can go get the DMA fences from all those DMA reservations, and then wait on them before executing the work. And then like the GPU work generates a new DMA fence, and we can put that in all the DMA reservations. And like if you do the CPU part of this somewhat atomically, like it kind of gets you a locking mechanism on the GPU. And you can use the exclusive fences, you can use the shared fences. Like on the AMD side, like we kind of conceptually always do the exclusive fence, but like there's drivers where you can say, hey, I'm writing this buffer, I'm reading this buffer, where you would do like exclusive or shared fences to basically do a read-write lock. But of course, hey, I'm the guy that's writing Vulkan drivers. So, and Vulkan is all about explicit sync and no implicit sync. So this is the exact kind of stuff that I don't want to do with my submissions. So how do we get rid of it? And so when AMD GPU is created, they had an interesting first step. So the AMD hardware has different queues that can run in parallel. Like we have compute queues, we have a graphics queue, we have DMA queues. So that instead of actually taking this setting the exclusive fence and stuff, they made everything like do a shared fence, and then let the driver determine things using a fence owner. So they extended the DMA fence like with the DRM scat fence, and that has an owner. And they basically said, hey, your address space or VM space of like the DRMFD is the owner of the fence, and we're only going to synchronize with fences that have a different owner. So that means that like within a single process, you've now basically killed implicit sync. Mostly. We'll talk about all the exceptions later. Of course, like half year into Red 3 development roughly, Valve came and said, hey, we want to do a VR composer with Vulkan and everything. And that has explicit synchronization. And now you're actually sharing buffers between processes. And they didn't want any implicit synchronization, which was especially visible at some point with high priority compute, like if there were any missed frames or anything like that. So we needed something more than this. So we added a way on buffer creation on the AMD side to mark a buffer as explicit sync. And those, like, to disable it, we basically say, hey, we don't wait on any fences at all if we can determine the owner. And it only exception is memory fences. So if the kernel is moving memory around, then it got a very, for like scaling to VRAM or from VRAM to GTT or something like that. Like it's got a very special owner that it always hard codes as always do. But otherwise, like we skip always waiting, but we still add the fences. And this is very annoying because you can't, like it really relies on all the submissions on this buffer participating, because otherwise you're still implicitly syncing somewhere. And that's going to be a problem later, because you can't just create this buffer and send it to a GL driver, because your GL driver totally doesn't expect to have no implicit sync at all. So that's like, hey, Vulkan to Vulkan, this works, but Vulkan to GL, this doesn't work. So you can't actually use this for the WSI or anything. Besides the fact that a lot of WSIs actually don't have any explicit sync to replace the implicit sync. And some other drivers have like, hey, if we want to do a submission without implicit sync, we don't touch the DMA reservation at all. And this has some limitations because now you don't know all your submissions anymore that touch that buffer. So like you have to do much more aggressive idling of the whole GPU if you want to actually move a buffer to some other place. So it's doable, but it has its own limitations. And so there are some remainder, like as I said, WSI buffers are still excluded. The other thing we had in AMD is mapping and unmapping buffers to the GPU address space was still very, very implicit sync. And in the meantime, we'd also grown a stuff where a DMA reservation may not necessarily be totally associated to a buffer. We have this thing where with the rise of bindless in Vulkan, sometimes you have like, I have 1,000 buffers that I'm just going to specify on every submission, and going to that entire list is very slow. So let's just make the kernel track that list and do very fast stuff with it, which include only having a single DMA reservation for the entire list. Which meant that we can't really use the explicit sync flag for anything related to this, because we're not actually creating a buffer associated with this DMA reservation. But there's been work this year to actually make it possible to clean this up. So Christian Koenig landed something earlier this year. This basically says, hey, instead of doing exclusive and shared fences in your reservation, we're going to have a couple more options. So like your write and read are your typical like exclusive shared thing that we had before, like with implicit sync. Your kernel thing is like, hey, if you have your memory move, then that needs to sync to literally everything, because nothing else can change or read things while we move memory. And then we have bookkeep, which is like, hey, we're using this, but we don't want to participate in implicit synchronization. So we have a couple more levels. And that allows us to now specify a lot more information. And we can actually use this to disable implicit synchronization everywhere in our Vulkan driver. We can just add a flag to say submission or some context or queue or whatever have you that you use for submission to say, hey, we should only wait on kernel fences and only set bookkeep fences. And yeah, we can stop marking buffers as explicit sync, except that we just break WSI, because there's a lot of WSI that doesn't have any way to send an explicit fence or sync file over to the display server or composter or something like that. And well, Jason added some new IOCTLs for this, where basically we can take a sync object or a sync file and say, hey, we take the fence from the sync file and put it in the DMA reservation and the other way around. And this way we can say, hey, totally independent of our actual submissions, we can now use the DMA reservation basically as a container for fences from user space as well. So kind of like the implicit synchronization mechanism now is a real side channel for communicating to your WSI for when is this ready for displaying and nothing else. So that's roughly a bunch of this stuff landed. A bunch of this is still in review on my side because memory management is hard, and I also wanted to kill the implicit sync on the memory with it, and we can totally do that because now we can say, hey, memory mapping only has to wait on like your implicit sync things, and bookkeep fences don't matter, except that for memory management you actually have to care a bit that your work is actually done before you destroy a buffer and stuff like that. So there are some corner cases that we have to worry about with stuff that we're looking at. But yeah, once this lands, I think we're finally completely implicit sync free in RedV, which is, I think, finally free of all those, like, we're partially there, partially not there, but we've hacked around enough that it's not a problem. And I'd like to thank a couple of people, Christian Koenig for doing a lot of the DMA reservation, DMA buff work on this, Jason for his new IOCTLs, and Daniel for pushing us all along to get this together. And that was my talk. Are there any questions? And not, oh, Alyssa?
Just have the question for now. Just have the question. So we're about to bring up two drivers. Since we can demand that we have the new kernel, all the new fanciness, we just be supposed to think from day one about all that?
Yes, so the question was like, since we're bringing up the new drivers, like for example, say, like, can we use this for explicit sync in our Vulkan drivers from day one? And I think it's totally ready for that. This thing works across all drives, is pretty horizontal. So as long as you don't build in any traps in your driver to still hit implicit sync, I think this is pretty doable. Jason says he will neck a driver if it doesn't. Okay, are there any other questions? Yes.
What's the main motivation for this work?
Okay, so the question was, what's the main motivation for this work? So implicit sync leads to surprises at some point when, like, it's kind of that we still have to enable this in over-synchronization issues. And sometimes over-synchronization doesn't really matter because, hey, it's exactly the same thing you're doing explicit anyway, but sometimes it's actually more synchronization and you're actually blocking stuff. So, like, one thing that can actually happen is, like, when we do bindless and you have all your buffers in your list and now you're writing Vulkan composters that keep your buffers alive, that then suddenly you care. But the more direct thing was actually the unmapping and mapping thing, where we had problems with games with sparse mapping and unmapping that streamed data in and out, where we had graphics work bubbles because actually page table work can take quite a lot of time of the frame, and with, like, basically implicit sync taking a lock, you couldn't do any actual useful work for the frame in that time. So Forza Horizon 5 is a game we extensively debugged that on, and we saw clear, like, hey, 20-30% of your frame is just page table mapping, that doesn't lead to a great experience. Yeah, obviously we want the page table stuff to be faster, but the easy way is like, let's just run it in parallel because we can. A lot of games actually, like, they don't do any further synchronization, like, hey, it's some mapping that's asynchronous and we just wait on it on the CPU. So it is very well parallelizable.
Are you saying that FH5 is now 20% faster?
So actually, no. When we benchmark it, like, the stutter is better, but the average is almost not moved. So it's like the periods that it's there, it's very bad, but like it's not moving the average much. Most of it, main benchmarking platform was the Steam Deck, and as usual, streaming is extra CPU work, which means less power for the GPU, which means like obviously your performance is still going to be lower on like a power constrained platform if the game is doing more CPU work to actually bring that data in. Okay, no other questions, then thank you all.
Hi everyone, my name is Erik and I'm an engineer with the Linux graphics team at NVIDIA. For the past couple of years, my focus has been on improving Wayland support in the NVIDIA driver, and to that end, I've also had the opportunity to contribute to several upstream projects like Xwayland, Wayland Compositor, and Wayland Compositors and some client applications. The subject of my talk today will be explicit synchronization for Linux display servers. I know that Bas will have described the difference between explicit and implicit synchronization and some lower level details in the talk before mine, but to start, I'd like to give an overview of some of the synchronization problems that are specific to display servers. In the typical case, client applications, games, video players, 3D modeling programs will kick off work on the GPU to render a frame to a video memory buffer, and then send a request to the display server to have that buffer presented to the user. That would be a WL surface commit on Wayland or present pixmap on X11, for example. The display server can then either pass this buffer directly to the output. In the case of a Wayland compositor, that might be a KMS driver controlling physical display hardware, or in the case of something like Xwayland, it would be a Wayland compositor. Or it will read from the buffer, maybe do some rendering of its own to draw things like window title bars and other desktop elements, and then composite that together with buffers provided by other clients into the final desktop image. In either case, though, to avoid corruption, we need to ensure that the client's rendering is finished before the buffer is actually made visible. Furthermore, when the server is finished reading from the buffer in the composition case, or it has been released by the output in the direct scanout case, we need a way to signal to the client that it's free to render a new frame into the buffer. There are other factors that can make the situation even more complicated. For instance, the system may have multiple GPUs, each driving their own displays, and so different portions of the desktop will be displayed on each one. Or the client application may be running on a different GPU than the server, as is often the case on hybrid graphics laptops. In these situations, we not only need to ensure operations on a single device are properly synchronized, but also ensure synchronization across devices. Or the user may be running a screen recording program like I am right now, or maybe a remote desktop server, and so buffers may also need to be passed to a video encoding library, again ensuring proper synchronization with rendering operations. So, how do we solve these problems right now? Well, at least with upstream drivers, access to video memory buffers is automatically synchronized at the kernel level. If one process, the client application in this case, submits some rendering to a buffer, an implicit fence will be attached, which will only be signaled when the rendering completes. If another process, the display server, tries to read from the buffer, the DRM driver will wait for the implicit fence to be signaled before executing the read. Or, as another example, if the display server renders the desktop on one GPU, and then copies a portion of it to another GPU to display on a different monitor, the copy will automatically wait for the rendering to finish. One big advantage of this approach is that it simplifies things significantly on the user space side. For the most part, the display server doesn't need to worry about synchronizing GPU operations. However, it also has some drawbacks. For one, it can lead to unnecessary synchronization. Suppose multiple clients submit buffers for presentation, and the server reads from each one to composite them together into the final desktop image. With implicit synchronization, it will be forced to wait for all of those clients rendering to complete each frame, meaning that the frame rate of the entire desktop will be effectively limited to the frame rate of the slowest rendering client. Additionally, synchronization can only happen at a per buffer granularity. Reads and writes to the same buffer will always be serialized, even if they access non-overlapping regions of the buffer. It's impossible to say render an image to one part of a buffer, and allow that to be read concurrently while you render a different image to another part of the buffer. More generally, tracking all buffer accesses in the kernel can itself impose a potentially significant performance cost. Currently in the NVIDIA driver, and I believe upstream drivers are also moving in this direction to some extent, GPU commands are submitted directly from user space, without needing to incur the overhead of calling into the kernel at all. But this model is effectively incompatible with implicit sync. Finally, it limits the flexibility afforded to client-side presentation APIs. For instance, it's impossible to have a presentation request wait for work which has not yet been submitted to the GPU, or to signal an implicit fence directly from the CPU, both of which are required to properly support Vulkan's WSL. So, given these inherent limitations of implicit sync, I argue that the best path forward for display servers on Linux is to try to move towards a more explicit synchronization model, where instead of simply relying on the DRM driver, GPU synchronization, both across processes and within each process, is managed in user space. So how can we do this? Well, the fundamental missing pieces are some sort of cross-process, user space visible GPU synchronization primitive, which can be shared between client applications and the display server, and the accompanying protocols to interface with it. The current implicit sync model is based on the DMA fence object, which represents a single synchronization point, such as when a particular batch of GPU work is finished, or when a buffer is released by a KMS driver. While these are exportable to user space as sync files, and so could be an option to base explicit sync on, by their nature they're somewhat limited in what they're able to express by themselves, and also may pose undesirable restrictions on the backing implementation. Therefore, a higher level construct may be a better candidate, and we do already have such a thing in the form of DRM synchronization objects. These were originally introduced to support Vulkan timeline semaphores, and thus they have almost identical semantics to those. Instead of representing a single synchronization point like a DMA fence does, they can represent a timeline of multiple ordered synchronization points, each associated with a 64-bit integer value. This allows for a greater degree of flexibility in how they can be used. With a DRM sync object, it's possible to wait for a given timeline point, even if the GPU work which would signal it has not yet been submitted. It's also possible to explicitly signal a timeline point from the CPU. So right away, this gets around two of the limitations of implicit sync that I mentioned earlier. Like DMA fences, sync objects can be exported to a file descriptor and shared across processes. Additionally, individual timeline points can themselves be exported as sync files or imported from sync files, allowing them to be incorporated into a poll-based event loop, which is particularly important for display server implementations, and facilitates interoperability with rendering APIs like EGL via the native fence sync extension, and Vulkan via the external semaphore FD extension. And while sync objects are currently implemented on top of DMA fences, essentially as a wrapper around one or more of them, with each one representing a timeline point, they are also conceptually compatible with other implementations. For instance, one can imagine implementing them directly on top of a memory-backed counter, which may be more in line with the user memory fences upstream is moving towards. Right now at NVIDIA, we're actually working on adding support for DMA fences in our driver, on top of a mechanism somewhat like that. Basically, to signal a DMA fence from the GPU, we'll submit a command to write to this in-memory counter, and then trigger an interrupt whose handler will check the value and, if needed, signal the DMA fence. And of course, this will also allow us to support DRM sync objects with their current implementation. So with DRM sync objects as the base primitive, all that remains is adding support to existing display server protocols like X11 and Wayland. I'll talk a little bit later about some of the current proposals for both of these. So, while we may have a path towards explicit synchronization, there are still some challenges that will need to be overcome. Firstly, it's always been the case that the Linux desktop exists as a collection of separate projects which all come together to create a working system. This is as true of the graphics stack as anything else. We have client-side drivers, X-Wayland, various Wayland compositors, KMS drivers, and so on, all developed by different teams with their own schedules. Thus, changes can't be expected to happen all at once. If the ecosystem does move towards an explicit sync model, it will happen over time in a piecemeal fashion. And so as individual components switch over, they'll need to remain compatible with other components which may still rely on implicit sync. Fortunately, the recently merged patches from JSON Xtrand offer an elegant solution to this. Briefly, they allow extracting a buffer's implicit fence as a sync file or importing a sync file into its implicit fence. So, for example, a Wentland compositor that uses explicit sync internally can still ensure proper synchronization with, say, a video encoding library to support screen recording, even if that library is still based on implicit sync. Another issue is safety. Ideally, a client application shouldn't be able to cause the server to hang if it never signals a synchronization point. With DMA fences, we rely on DRM drivers to ensure that the fence completes in a reasonable time, if necessary, using some sort of hardware-specific GPU hang recovery mechanisms. DRM sync objects also enforce their own timeout when waiting for unsubmitted timeline points. One problem that remains to be solved is how to fit the wait for submit and signal from CPU capabilities of DRM sync objects into a poll-like interface like we can do with sync files. Currently, these only support a blocking wait operation, but that isn't great for display server implementations, because we don't want to stall the entire server waiting for one client's timeline point to be signaled. It may be possible to handle this entirely in user space using something like a background thread, but that introduces a lot of complexity, and so ideally we may want to extend the kernel-provided interface somehow. Finally, most display servers currently use OpenGL to interface with the GPU. And while extensions like EGL's native fence sync do provide explicit sync capabilities, overall the API is still fundamentally oriented around implicit sync, unlike Vulkan, for instance. So if we want to avoid having to still pay the price of implicit sync after moving to an explicit model, we may want to specify to the OpenGL implementation that explicit sync isn't necessary for certain buffers. Looking at all of these challenges, though, none of them seem fundamentally intractable. And indeed, in some cases, workable solutions already exist. Hopefully by this point, I've made a reasonable argument for why moving towards an explicit sync model is something we should pursue on the display server side. To conclude, I'd like to go over some of the work already being done to this end. For my own part, I've tried to make progress on the X11 side by proposing additions to the dry3 and present extensions, adding support for explicit sync based on DRM sync objects, along with an implementation for Wentland. Because realistically, even though the Linux desktop is transitioning to Wentland, X11 applications aren't going away anytime soon, and so Wentland will likely remain an important part of the graphics stack for the foreseeable future. These protocol additions introduce sync objects as a new protocol type, importable from a file descriptor, and allows specifying acquire and release timeline points on a given sync object for a present pixmap request. To avoid having to stall either the CPU or the GPU on the server side, we're able to export a sync file for the acquire point, add that to the server's event loop, and thus defer execution of the request until the timeline point is signaled. Then, after the pixmap has become idle on the GPU, it'll signal the release point. And while I've only added such support to the present pixmap request for now, having the basic sync object primitive in place could allow for other use cases. For instance, the damage add request could be augmented in a similar way to allow for GPU synchronized damage reporting. On the Wentland side, while we've actually had an explicit sync protocol for some time based directly on DMA fences, this hasn't been widely implemented by compositors, and as mentioned above, DMA fences alone are a bit restrictive in what we're able to do with them. Thus, Simon Sur has proposed a version 2 of this protocol based on DRM sync objects instead, and has also shared a work-in-progress reference implementation for WL roots. Indeed, I tried to mirror the design of this protocol in my own proposal for X11, hoping that this will both make it fairly straightforward to add support for the new Wentland protocol in Wentland, and simplify things for client-side drivers, since X11 and Wentland would be using similar mechanisms for synchronization. Also, Michel Danzer has shared a patch for GNOME's Mutter compositor to have it explicitly pull the implicit fence of client-provided buffers before compositing from them, which solves the issue I mentioned earlier, where the server's frame rate can be limited by a slow rendering client. So in that case, we can see that some of the benefits of explicit sync can be realized even with only part of the stack using that model. And finally, although perhaps a less general application, Crostini, which is used to run Linux applications in a virtual machine on Chrome OS, also uses explicit sync when interfacing with the Wayland compositor on the host system. It operates by piping Wayland protocol between the host and the guest over a Vertio interface, and relies on the DMA fence-based version 1 Wayland explicit sync protocol, along with JSON's implicit fence import-export ioctls that I mentioned earlier. And here I've just included a few links to some of the merge requests that I just mentioned. As a closing thought, the transition to explicit sync will almost certainly be a gradual process in display servers, client-side drivers, and any other GPU interfacing components. But I do believe it will eventually leave the Linux graphics ecosystem in a better place going forward. And while I've shared some of my own ideas on how we might get there, ultimately all of the parties involved will need to cooperate and agree on a solution that works for everyone. I'm confident that this is achievable though, and I'd just like to add that we at NVIDIA definitely would be interested in being part of the discussion. So thank you all for listening to my talk. Thank you to the XDC organizers for putting together a great conference, and I'd be happy to answer any questions.
Hey, so we should have you now on the screen. So can you say something just to be sure that the audio is coming through?
Yeah, testing.
Okay, I'll make you a little bit louder. Can you try now?
Testing.
Yeah. Okay, all works now. So let's
Yeah.
see. We don't have any questions from the chat. Are there any questions in the room? Okay, looks like we don't have any questions for your talk. So thanks for sending your presentation and thanks for joining us in person for the Q&A. And that will be it.
Sure, thanks everyone.
Thank you.
Hello there, everyone. I'm Ryan Houdek, and I'm here to talk a bit about the FEX-Emu project and some of the interactions with the ecosystem that it has, because it is a bit strange. So first of all, who am I? You may know me as HDKR in the IRC. I've worked on emulators for more than a decade now, and I mostly focused on the portability concerns around them and then porting them to ARM as I do. I started working on FEX-Emu in early 2019 because initially I was interested in learning x86 assembly because I had never touched it before. Boy, was I in for a job. So I'm going to keep this fairly short, but what is FEX-Emu? It's a user space only emulator that translates both 32-bit x86 and 64-bit x86 into ARM64. This has the quirk that any 32-bit application actually runs as a 64-bit application and all of the problems that that entails. We only do Linux on Linux translation, and at the moment anyway, and hooking up some level of wine thunking is not out of the question. And the major driving goal behind FEX is that we need to be fast enough to run a wide variety of games, well, applications with games being of a particular interest for backwards compatibility. Last I looked, there's something around 75,000 games on the Steam platform alone. And barring any video driver compatibility issues, it'd be great to have more than 90% compatibility with these. Our CPU emulation uses JITs to get the performance that we need. And FEX is under very active development, and we're smoothing out a bunch of the rough edges that we have. Similar projects that you might have heard of would be Rosetta 2 on macOS. Microsoft has their XTA layer for Windows. And QEMU has a user mode emulation layer that's very similar. We're licensed under the MIT license, and that's for granting as much compatibility with any side project that needs to use us as possible. And while emulation ends up looking like a bunch of sorcery of assembly translation, we're mostly going to stay away from all of that, because that's all the scary inner things that don't really matter for this, and focus solely on the ecosystem issues. Well, we'll mostly stay out of it. So, with FEX emulating the CPU architecture in user space, at some point we need to cross that architecture boundary. And in order to do this, we can do one of two things. We can either do full emulation of everything x86, so the program, its included libraries that it ships, and any system libraries that it manages to pull in, all the way down to the system calls. And it's at that point in which we can cross the architecture boundary, and we do syscall translation or potentially a little bit of emulation there. This is the most compatible path, and it's what FEX will do by default currently to retain as much accuracy as possible. This is quite good for testing and any lightweight games. They can have enough performance in this case. But for anything remotely heavy, we need to do something more than this. And this is where library thunking comes in to give us a significant performance improvement. So when an application loads a system library, we can actually just capture that and replace it with a shim thunking library where every API call ends up being a call into a native ARM64 library. So we're crossing the architecture boundary at the API level rather than the system call level. I'll come back to explain what that means in practice. So let's start off talking about what happens when we're running the fully emulated path. Again, all the game, the libraries it ships, and the system libraries are all emulated. While FEX's CPU emulation, the syscall translation layer, and a light file system emulation layer actually all run natively. It has significant overhead because of all the CPU time that ends up in system libraries. And we're required to compile Mesa drivers for x86 that typically wouldn't have been. So this means drivers like Turnup and Panfrost are compiled as x86 libraries, and they're equivalent 64-bit, to run inside of this emulated environment. And we've been mostly lucky so far that this actually works in Mesa. But if you're running on something like an NVIDIA Tegra platform, That just won't work because NVIDIA doesn't ship an x86 library that works on Tegra. This has a nicety that the footprint for what we need to translate across architectures is actually relatively small. With everything being delegated to system calls, we'd basically just have one location where we need to cover. And it's absolutely critical since we can't mandate what the application ships itself. It can do any syscalls it really wants to. We've seen games that actually just like ship half of a distribution themselves, libx11, libgl, whatever they have. And that breaks spectacularly because whatever version of Mesa that they happen to ship just doesn't have any ARM GPU drivers because it's x86. So for Mesa, we're building so many of these drivers that have just never been tested under this weird configuration. And they work pretty well, even though they've never been tested. We've tested Panfrost, Adreno's drivers, and the Broadcom drivers so far. But what does this mean for the average Mesa developer working on these ARM-based GPU drivers? First thing to keep in mind is please don't optimize for this case. If you're benchmarking x86 games and you're in this configuration, don't write x86 specific optimizations in ARM drivers. It kind of goes without saying. Because we're going to skip over the library thunking anyway. It's the exception that users won't have to deal with this and they won't have to contend with it long term. That said, if someone is optimizing some CPU routines that do take a lot of time, just make sure it still compiles in an x86 environment, do the proper architecture checks, and then make sure it just goes down the C path. It's a very useful configuration for debugging because it just gets a lot of bugs out of the way. And big thanks for accepting that patch that enables the SSC path for floating point math. Reducing any usage of the x87 floating point model is just a huge win because we don't have to go down a soft float path for 80-bit floats. So what is our library thunking and how does it work? So we replace the system libraries with a shim library, and it marshals data over to a native ARM64 library. So if an OpenGL application calls some GL draw on the x86 side, what it's actually doing is it's passing that data directly over to the ARM64 driver through our thunking magic. It's fairly lightweight compared to something like Virgil, since the overhead mostly appears like a regular function call, but with some data marshaling overhead for repacking some data. Although this does have a weird interaction with the windowing system, which is quite error prone with pulling in X11 symbols, and we're still working out some of the quirks there. A nice side effect of the library thunking is that we can kind of hit each library that takes CPU time piecemeal. And by only thunking a library at a time, we can mostly just target libraries that an application spends a bunch of CPU time in, and let the rest just be fully emulated as usual. Of course, the more thunked libraries that we implement, the less time we spend actually doing CPU emulation, thus giving us more performance and more power savings. Although this starts hitting diminishing returns very quickly past the graphics drivers. To see how much time is actually spent in emulated libraries, FEX actually hooks into the perf interface and starts generating perf symbols so it can coalesce and collapse all the library time, which is super nice for just figuring out what you want to do next. So how is this different for Mesa developers, though? From the Mesa developer's perspective, it's mostly ideal. When you're writing your driver, you won't see any of this x86 shenanigans that's going on in the background. Everything just effectively is native ARM. Although there is two glaring changes because of FEX. There's virtual address space differences that end up cropping up. And all of these ARM drivers are now susceptible to x86 bug reports from x86 games. And I'm sorry, but reproducing reports in this environment is really tricky. It's kind of difficult to set up. And so most things will be delegated to captures to try and ease the burden of actually testing these things. So let's talk about the virtual address space differences here. Some very large implications depending on if the user space driver or the kernel driver starts making assumptions about how much virtual address space is available. So as said earlier, FEX translates both 32-bit and 64-bit to ARM64. And while we're translating the application, we need to make sure that the virtual address space was what the original application was expecting at the time. So ARM supports multiple different configurations of virtual address space, depending on what has been configured in the driver and what device. And the user space ends up supporting anything from a 64-bit virtual address space all the way up to something as large as 52-bit currently. 39-bit and 48-bit are mostly what we care about in the consumer space. The rest are kind of special cases. So with 64-bit x86, the user space is only given 47 bits of virtual address, and that's the total of its 48-bit virtual address space. The kernel living in the upper 48-bit space, or the upper 128 terabytes. So 256 cut in half. So when FEX starts, it needs to allocate 128 terabytes of virtual address space potentially to ensure that no x86 addresses ever get allocated inside that range and then crash the runtime. A real example of actual code breaking here is the Go programming language doesn't canonicalize 48-bit addresses correctly, so anything in 48-bit space just crashes their runtime. This allocation on the FEX side isn't actually that large of a concern, because we still do have 128 terabytes of virtual address space remaining, which matches what x86 has. The real problem starts arising when we're running 32-bit applications. In this situation, FEX is going to allocate all 256 terabytes of your virtual address space and then leave a 4 gig gap at the very beginning. So as you can see in the little image, you just see tons of virtual address space being pulled in there. This is, of course, because 32-bit apps only have 4 gigs of space. So if a driver decides that it wants to handle virtual address space differently, depending on if your driver is currently 32-bit or 64-bit, then that's when problems will start cropping up. Because from FEX's point of view, we know it's very simple to start allocating tons of virtual address space, because in 64-bit space, it's plentiful. But your library is now just an ARM64 library with 4 gigs of virtual address space. So you kind of have to be careful around this. In practice, we haven't actually run into this issue, but there's always a chance. And one thing I haven't looked into is actually how much physical memory is being used in the kernel for tracking all these allocations. The kernel will do VMA merging so that that isn't consuming a bunch of memory. But when you're programming the MMU, I'm actually not sure how much is being pulled there. And typically ARM devices don't have a ton of RAM to begin with, so it's kind of rough. So we talked about the user space. Now let's talk about what happens with ioctls in our translation of that. The major annoyance is actually in our syscall emulation, where we're translating ioctls across the architecture boundary. And we need to know what sort of ioctl that is being talked to. So this requires file descriptor tracking and struct repacking for any sort of ioctl that doesn't actually match across an architecture. In practice, this means that FEX has local descriptions of around 700 different ioctls, and we have a script in our CI that tries to ensure that we don't miss any of the definitions. It'll ensure that all the data packing ends up matching across the architecture, and when it doesn't, we have some handler that'll actually hook it up. And this ends up being exactly the same as how our thunk repacking works, except we're doing it for ioctls instead. So ensuring we have 100% coverage of ioctls is actually a really rough task in user space. So most of our effort here is just around DRM. In most cases, DRM has been pretty good at keeping the ioctls definitions matched across the architectures, but it's not completely smooth sailing. It mostly comes down to older ioctls using raw pointers or messing up the packing between different members with alignments. The silver lining here is that when we're using library thunking, almost all DRM ioctl problems go away because we're thunking both OpenGL and Vulkan. And the problem remains with other libraries instead. Then as a side note, once Asahi, Linux's DRM, settles in, I'm going to run their interface definitions through our scripts to ensure that it actually works. I'm not expecting any problems, but it's always good to catch these things early. So at the end of all this work, what do we have? We finally end up with the payoff. x86 games running fully on ARM GPU drivers and on their respective hardware. My testing platform of choice today is the Snapdragon 888 because it has turnip, it has Readreno. It's very good. It's a pretty powerful GPU. But just because it's powerful doesn't mean everything works perfectly. The biggest class of bugs typically come down to tiling problems. Massive rendering artifacts where you're able to see the tiling issues. Usually comes down to games abusing the API incorrectly. But in some cases, it can actually find a real bug that needs to be resolved. One of the bugs we actually had recently was alpha to coverage wasn't working correctly, and we fixed that just recently. So this is a case that PC game developers just haven't ever had a chance to test their games on, of course, because they just can't run on this class of GPUs. And running these games on ARM, they're not going to port their games to it. So you have to be delegated to API captures on an x86 device. So Snapdragon has a fun issue currently, where if you disable vsync, you can actually see all the tiling bugs around the vsync tear, which I find to be fun and very interesting. Another issue is that almost all of the PC games that I've been testing require GL 3.3, anything fairly recent. So if the driver is limited to GL 3.0, a lot of games actually just end up just closing early or crashing because they're just using the new feature and breaking. And the good news here is that if you have a Vulkan driver available, then Zink works really well for exposing OpenGL 4.6. And it's pretty performant under emulation from what I've seen. But that's only half the story, because that's all native Linux games. A significant number of games on Steam are Windows games running under Proton. So this is shipping VKD3D and DXVK, the Direct3D translation layers that require very new Vulkan features. So FEX-Emu running the latest AAA games on ARM devices aren't too far-fetched. And having a competitive Vulkan 1.2 driver is going to be very important in this sort of ecosystem. So I'm not going to go into too much detail about how the thunks are implemented, but it ends up being that the x86 application will do a function call, or it'll do a function call to what it thinks is the real library function, and it's actually a function in our shim library, right? The thunk function will pack all of its arguments into a struct on the stack, and then it'll execute an invalid x86 instruction, which our JIT compiler will actually capture that, and it'll redirect it to the known good ARM64 function entry. And it behaves exactly like a call instruction where it sets up the stack and then it'll return at the end. So the ARM function on our ARM side of the thunk will unpack the struct, and it'll call the real host side function, and then it'll return the result back to the x86 side, and then it continues as normal. The current 64-bit x86 thunks we support are OpenGL, Vulkan, the x86 libraries that need to go with that, and VDSO. And we just implemented our first 32-bit thunk with VDSO last week, and the rest are sure to follow. VDSO is very simple, so it exercises most of our thunk infrastructure without a bunch of the other complexities. A trickier detail is that we also need to support callbacks from the ARM library calling back into x86 code. OpenGL's debug callback interface is a good example of how this works. There's a bit of finicky magic there, but it works as expected. So one thing I haven't really investigated nearly enough is what video decoding happens in games. I know a lot of games will use software video decoding, but What if they want to use a hardware video decoder? ARM devices typically are just wiring up v4L2, whereas all the desktop chips are running on VA API and VDPOW, and Vulkan video is coming at some point, hopefully. There's a lot of need here for investigation and just testing games to see what they want. I'm sure some people know what it is, but we might need to actually wire these up to make it more seamless. So the work on FEX is never ending. And so looking to the future, what are the things that we plan on working on? Thunking optimizations is something that will come sooner rather than later. With a bit of work, we can actually remove a bunch of the stacked struct object generation that we're doing, and it ends up being even lighter. The Wine folks have been working on their PE conversion for their libraries for a while now. Last I checked, this work is mostly done, and it might be a good time to start actually looking at how to integrate into it. And the interesting idea here is that when Wine jumps from its Windows DLL to the Linux shared library, we can insert a thunk at that point and get cross-architecture thunking set up and running inside of Wine pretty quickly. And this should accelerate Wine games on ARM once implemented. There's still an open question about exactly where we want FEX thunks to live in Wine. Preferably, we want them to live as close to the PE library's entry points as possible, because any sort of emulation can be removed at that point. It may not be desirable. We just need to have some discussions about figuring out where we want it. And there's some work here to actually stabilize FEX's thunking ABI so external projects can't actually use it. Probably with some symbol versioning to make sure that if we need to break anything, we don't actually just outright break everything. And there might be some more work on the Wine side to hook up to our infrastructure to have function signatures in the way that we need them. But that's just work. And of course, the eternal struggle with emulators. More performance, more compatibility, more everything. All right, so now I'm going to do a quick demo. It's a recorded set of games on my Snapdragon device. And they just got running like last week, so it's pretty good.
Ah, a visitor. Stay a while. Stay forever. I mean, stay as long as you wish, and I will tell you a story of wizards. Just Ah, a visitor. Stay a while. Stay forever. I mean, stay as long as you wish, and I will tell you a story of wizards. Just wizards, no vampires.
So, Alex, the day's finally here. You've been at the Helping Hands group home for 8 years. We've been through a lot in that time.
We have.
that's it for that. Let's see here. This just went all over the place. Okay, so where to find this? With that, here's where to find Vex. We already have some users hammering away on this. I'm sure you can find some use cases for it at some point. And I want to thank all the people that have actually contributed to the Vex so far. Without their continued support, it just would not have been possible. And there are stickers in the hall. Please take them away from me. I don't want them. I have too many.
GFXReconstruct itself, if you want to talk that, it needs to talk to Wentland and stuff, so ideally it would be dunked from the PE side and not the Unix side, but I guess there could be something that goes back the other way, but could we do it from the PE side or something like that?
Yeah, so the question is, can we actually implement something like Microsoft's ARM64CE or EC ABI for Wine, so we can keep thunking that on the PE side rather than the Linux side, specifically for Wine Vulkan. There's probably a way we could do this. We're already just setting up our cross-compiling environment to compile into a Linux ABI. I think compiling over to whatever Microsoft's ABI is for the ARM side shouldn't be that hard to do. And we could go both routes. We could still thunk on the SO side for initial testing and then switch over to PE if it ends up being more optimal.
Would it be useful to set up build testing in SSCI to make sure that the x86 build of the drivers that you need works?
Yeah, so the question is, would it be useful to set up a x86 CI in Mesa in order to ensure that what we're currently doing with ARM devices on x86 would still work? And yes, that is very important to do, I think. We should probably talk about actually setting that up.
Should be fairly easy.
Yeah, just cross-compiling.
Maybe it's a little like beyond the scope of your presentation, but what kind of things have you seen in terms of x86 ISA specific, like, I don't know, corner cases or undocumented behavior? That's the first question. The second question is, what kind of, there've been like, over the last maybe 30 years, there've been many attempts to do x86 instruction emulation. Some are like software-based, like FX32, if you know. I should know what FX32 is. Another one that's more hardware approach was, I'm sure you know too, the transmitter Crusoe. That was about 20 years ago. Pretty noble approach. You know, it didn't work out for whatever reason. So what kind of internal, I know you know, that is kind of beyond the scope of your presentation because it's more graphics oriented, not the internal technology of your FEX-Emu thing. What kind of approach you take internally in terms of like x86 instruction, like interpretation and caching? Is it similar to like Crusoe in some ways?
Okay, so the first question was, what sort of ISA quirks have we run into? So this one's actually really interesting because some of the instruction implementation details will differ depending on vendor, and they have different edge cases or even definitions as to what the instruction should do. So we usually just pick one of the models, and you have one hardware's edge case. But yeah, we've definitely hit a couple.
Which vendor? You don't mind mentioning.
Oh, both. Yeah, they both have different definitions as to how things should work depending on if it's 32-bit or 64-bit.
Did you, like, I know it's a pretty very minor, but did you look at the nominal processor? I mean, that's a third that say suspended in some way. That was extremely minor. Did you look at for like analysis?
So we have looked a little bit at VIA, and we are actually abusing one of their undocumented instructions for our thunking infrastructure. We're using the alternative instruction that they had on one of their models. But I haven't actually done any hardware testing to know what sort of differences they have.
What about the internal technology? What kind of approach is it similar to like Rousseau's approach of the cache instructions that already been like scanned and interpreted?
Right. So the internal technology of how the JIT compiler works, and how it doesn't map to what sort of transmeta was doing in the past. So since we're an entirely user space application, we of course don't have any sort of piece of hardware that's actually running a firmware translating these instructions. It basically ends up looking like a fairly complex JIT that uses an IR, similar to how QEMU has TCG in the back end. And we'll cache any sort of basic block we hit up front, and we'll cache it for that process. And we're working on saving all of that to disk, so future processes executing the code will not have to hit that JIT runtime cost. Additionally, there's some interesting ideas around actually ahead of time JIT compiling all of the libraries if possible. It's not always the case. Some executables are encrypted, and relocations actually make it kind of tricky to do it up front. But other than that, it's just a JIT.
Okay, last first question, last one. Did you have to deal with self-morphing code, self-modifying code? Maybe that's a little bit, maybe some people never heard of it, but they used to do it long time ago in x86, and in order to ensure x86 compatibility, apparently it's pretty tricky to kind of test those things or getting it right. Did you have to do that?
Yeah, so the question is, did we have to deal with self-modifying code and self-morphing code? So definitely. Web browsers today still use self-modifying code, and they'll backpatch and they'll do crazy things. Any of the code that ends up being executable and they change it over to writable, or it's always executable and writable, we do mapping of those pages as read-only. So if it gets modified, it'll actually end up invalidating our cache, and then we end up rejitting the code so we can handle the new state. Because the problem ends up there being that since x86 is a strong memory model and they're coherent all the way down to the iCaches, depending on which hardware you're running, you just have to do that. You have to handle it because people just write new code in memory wherever they want. And it's a common thing today. Denuvo does it, other DRM does it, web browsers. It's all over the place.
We have a question from live audience, but does it run Crysis?
So the question is, does it run Crysis? And the answer to that is actually yes. It does run Crysis. It runs both the 32-bit and the 64-bit version. It depends on which Wine version you're running, if it'll actually work. There's some memory corruption that we're running into that we need to resolve, but it runs.
I'll try to stack while this is close. How much did memory ordering constraints, differences between them? How much of a pain is that?
Yeah, so the question is memory ordering constraints, and then that'll lead into the difference in memory model between x86 and ARM, and how much of a pain that is. It's the biggest pain. It's the worst. Everything turns into atomics, because that's how you have to emulate it. And there's really nothing you can do, but ARM does have a few extensions for us to try and alleviate some of the pain. In ARM v8.1, they added memory atomics directly, which help us out because x86 can modify memory directly. They added the RCPC instructions which more directly map to how x86 works, but there's still the issue of alignment. And x86 just allows unaligned anything within a cache line. And Intel even allows unaligned atomics across a cache line with split locks, of course. So a newer version of ARM allows us to do unaligned atomics within a 16-byte granularity, which isn't quite a cache line. And when we're emulating everything, we're just catching the alignment faults and emulating it inside of the signal handler. It's a pain. Absolutely terrible.
So I have heard of Box86. I just now heard about FEX. It seems like you're both working towards a similar thing. Are you using Box86, or is it just like a different implementation of simulation on or I guess what's the difference between the two? If I'm going to run a game on.
Okay, so the question is, what is the difference between Box86, Box64, and FEX-Emu then? To answer the question of are we using Box86, that is no. We are an entirely separate project using our own JIT technology that we wrote ourselves, and Box86 is independent. For comparison's sake, if you want to choose Box86 or FEX, they're both probably good choices, but FEX would probably end up having a higher compatibility, whereas Box can end up having higher performance currently. So it's a bit of a trade-off which route you want to go. And we're working very hard to make up any sort of performance difference we have. They emulate the memory model slightly differently than us, and the x87 slightly differently, so there's just trade-offs. Sounds like everything. All right, thank you very much.
Hello. Is that good enough? Hey, everybody. Used to lapel mics, so this will be fun. Thanks for coming to the session. My name is Brad, and I'll be talking about GFXReconstruct, which is a tool suite for capturing and replaying essentially Vulkan calls. We have a copy of our slides on our website, but of course they're up on the XDC site as well. I'm going to go through a brief overview of what this thing is, talk about what the use cases are, and why you'd want it. I'll go through how you capture, replay, and use other tools on streams. I'll go out a little bit into the architecture depending on how tired people look and how hungry they look, and then try and do a live demo. But first, and I realize I won't be seeing hands up from YouTube, but how many people have actually used GFXReconstruct here? That's okay, that's not bad. How many of you have used it just from the SDK, the Vulkan SDK? How many people built it from source? Okay. That's a lot. Okay, that's probably about half the, third to half the people. Okay, so some people are going to know what this is and some people aren't. The source code is available on GitHub, so you can go and take a look at it now or whenever you'd like. But the fundamental thing is it captures Vulkan commands to a file and then allows you to replay them. The source base is in C++ with some Python generators, since we use the Vulkan XML to generate encoders and decoders and the things that actually replay the commands. Runs on Linux, Android, and Windows. It's designed to be API agnostic, so the idea is that it could do OpenGL, could do OpenXR, but right now what we have is Vulkan. And then there's a handful of additional tools as well as capture and replay. There's a lot of different use cases. The one that we see the most is regression testing. So people will take a capture of an application or a game, and what we store is all the Vulkan calls essentially verbatim, and then replay them as closely as they can be replayed, which is not always possible, but we try to do the best we can. Other reasons you might use it are for bringing up silicon, which includes architecture simulation, bringing up the first passes of things in FPGA or whatever, and finally for bug reporting. So if somebody wants to run a game and they know that there's an issue on a driver with a particular Vulkan call or a series of calls, what you can do is just take a capture and then send that to the platform vendor or whatever to take a look at. So we provide this thing in a Vulkan API layer. How many people are familiar with the way the loader works on Vulkan? Okay, I'll just mention then that the Vulkan loader does this work of bringing in shared objects to hook basically between applications and the driver. And we use that facility to basically just catch all the Vulkan calls in Core 1.3 and many useful extensions, but not all of them because there's a lot of them. We capture most inputs and outputs with a particular exception. If the function call returns an error, then we don't store outputs because those outputs would be invalid. And we also don't store some inputs that are also outputs. So you may be familiar with the to-call idiom, where the first call is you find out how much space you need, and then the second one is you actually make that call to get that data. We don't store the inputs. We only store the outputs from the driver. An example is enumerate device extension properties, where you pass in the number of extension properties that you first ask how many, and then you allocate the size of the extension properties structures, and then you pass those in. I was afraid of this. I'm getting warm up here, so I'm going to take this off. So probably the easiest way to use GFXReconstruct is through the Vulkan configurator, vkconfig, which is a GUI tool. And I'm going to ask more questions. How many people have used vkconfig to do capture? Oh boy. Okay. So how many people then are using the instance layers environment variable to do it? All right. So, and then how many people use the actual command line tool GFXRecon.py? Not a lot. Okay, so most people, you're all interacting with it through the instance layers and the environment variable. That's interesting. That's the way I do it, but I assume that's because I'm not very good with UI applications. Okay, great. So if you're going to capture, there's a couple of options that we offer. A Vulkan application can map memory, write what they want into that memory, and then unmap it. And that's the way you provide textures and vertex buffers and other data. But you can also map it and then just not let it go. So if an application does that, we need to track what's changed and store that in the capture file. So by default, we mark pages read-only and then detect through a signal handler when those have been changed and write those out. That's the default. You can turn that off. We've had cases where some applications and engines interfere or delete our signal handler. So if that's the case, you can use assisted mode if an application uses flush mapped memory ranges, which not everybody does, or just fall back on unassisted. And so that means that every time there's a draw call, we just write all buffers all the time to make sure we get any changes that were made. But that's frequently impractically slow. We also support trimming. So you don't want to have to capture all of an application or a game and then replay all those frames. You'd rather just play back the frames where there's an issue that you want to review or something that you want to run for regression. So we can capture multiple frame ranges or use a hotkey on desktop systems. On Android, we don't support that yet. All graphics state up to the range that's being captured is tracked. And then when we begin the trimmed range, there may be several, the tracked state is stored in the capture file. So in this example here, I want to trim to frames 1, 2, and then 10 through 20. So I'll get 3 files for that. And each one will have state set up for each of those ranges, all the way to 1, all the way to 2, all the way to 10 to 20. We are a little bit conservative. We don't know what future frames might reference. So we end up storing in the capture file everything that exists up to that point. We do have a tool for optimizing away those things, and I'll describe that a little bit later in the slides. Okay, you have a capture, you want to replay it. We do attempt to replay as close to the original as possible. The one thing that these systems have these days is you can have embedded, of course, a GPU and the discrete GPU in your laptop, or you can have a system with multiple GPUs. And so if you capture a stream, you get it on the GPU that was chosen by the application. So to replay it, you can provide -- GPU, which uses the index, I believe, that comes out of enumerate devices. And that way you can choose exactly which GPU to replay on. You can replay on a different driver version or a GPU model or even a GPU family, but these are all tricky because an application, especially in Vulkan, chooses extensions and settings which are very specific to the GPU, more than it would have ever been in OpenGL. So we support a couple of ways to help with that. The primary one is to do memory translation. Memory translation. So the two most important ones, I've got 3 written down here, but the 2 big ones are remap and rebind. So for remap, we take all of the memory types that were captured and try and find mappings to those for the memory types in replay. And then when a memory is allocated, we just change the mapping type, which is pretty high performance, but may not be very accurate, which is to say it might crash. So, or just give you wrong data. Rebind is the more interesting option to use. It defers all allocations until that memory is used, and then uses Vulkan Memory Allocator in order to reallocate with the right alignments and the right settings and the right types. But that means their performance might be a little bit slower. This is kind of my private favorite option, this remove unsupported. When you create an instance in capture, you provide a list of extensions. So in replay, normally we just pass that list of extensions through, but driver versions change the number of extensions available. Some go away. An example was VKKHR ray tracing was a provisional extension for a while, and it was split into 3 different ones. So we have some captures in our CI system that ask for this extension, but then don't use it. And so in order for us to replay it, we use remove unsupported command line option, and that goes and removes any extensions from the instance creation that don't already exist on this replay device. Of course, if an application uses the extension, all bets are off. We do warn if in replay a function returns a different return code than it did in capture. That's usually an indication that something's potentially wrong, but often it could just be like an event hasn't returned yet, or something returned a slightly different value, which is still valid. In the case that a captured application made allocations that failed, then in replay, we'll try and make those allocations too, and sometimes they succeed. And so what that means is that the memory access pattern changes on replay. So to prevent that, you can provide skip failed allocations, or SFA for short. And that means that anytime an allocation was made in capture that failed, we just don't do that on replay. On Android, we only make one surface. So for a capture that was created that opened multiple surfaces, you can choose the index directly. You can save off screenshots, all of them, or some range. An interesting feature that was merged recently is virtual swap chain. So you may not know that swap chain acquisition index order might change even on the same GPU and the same driver if you're using mailbox or immediate present mode. So when the application is being captured, it's setting up all of its rendering state and all of the rendering targets using these handles. But those are not necessarily linked to the index that's returned from acquire. So when you do the replay, it may actually just render the wrong thing because we're filling up all the data and rendering into render target and then acquiring something different and presenting that to the screen. So virtual swap chain virtualizes that access. And in fact, we discovered, and I think this is right, but someone can correct me if they know it's wrong, Android 12 and 13 potentially change the number of swap chain images that are returned. So then all bets are off there. There's nothing you can do unless you use this virtualization. And finally, although I think this is mostly just used by me for testing, you can even request that a replay on a different platform use that platform's Windows system interface. Like I had a Linux replay, Linux capture that I was trying to debug, and I was able to replay it on Windows. But of course, the extensions are pretty specific, and so that doesn't always work. Other tools in the suite include info, which is pretty straightforward. It just prints the number of frames in the capture, prints other information about it. Optimize, I was mentioning earlier, when we trim, we just store everything. You can run optimize on a capture and that'll produce a new capture by basically marking all of the resources that are used and then not copying over the ones that aren't used. You can change the compression format. A kind of a fun esoteric one is extract. It'll take all the shader binaries out of a capture and store them in a directory so you can look at them, or you can alter them and then replay the capture, changing the shaders in them. But that's advanced use, I think. And finally, we have a new tool. We've been working on it for a little while. It'll be in the next release called Convert, which produces JSON lines output for a capture. So every function call from Vulkan that's in a capture, we produce a detailed one per line. So it's not exactly readable, JSON record for the function. And I'll show that at the end if I can get that to work. So we have a file format and we lock it down. Recently, we've been trying to make sure we deprecate blocks and don't change things so you can always replay old captures. And I was going to go through this slide and talk more about what those are and what those look like. But really what I wanted to say was we don't really tell people what they should do is read a file. What we tell people they should do is take one of the tools we have, which uses a consumer, and make your own copy of the consumer. And then you don't have to worry about what's in the file. You don't have to worry about the file format. You just subclass the consumer and we take care of all that for you. I'm keeping track of the time and make sure I don't dive into too much detail here, which is my trademark. The capture manager component deals with API specifics, anything which is not an actual Vulkan call. The encoder is a base class which is meant to serialize API call info and parameters, basically puts them into buffers. On the replay side, the file processor object knows how to read blocks from a file, but it doesn't know what's in those blocks. It doesn't know what's in any of the Vulkan blocks. And it knows how to decode and uncompress and then call decoder subclasses. Those decoders know how to deserialize the API call info for something like VK create image view. It knows how to pull out all the parameters for those. And it takes those parameters and calls consumers. The most obvious consumer is the Vulkan replay consumer, which takes those parameters, may mess with them, and then calls Vulkan directly. I think the directory structure is fairly straightforward. The one thing I wanted to point out is that we generate a lot of code from vk.xml, the encoders and decoders, and some of the consumer code. And we do that by hand. And the reason we do that is that we've had a couple of experiences where the structure types and the layout of the structures in the Vulkan header changed. And so if we don't keep an eye on it, what you'll do is you'll have an older version of the code which wrote one struct to disk, and then a new version which reads a different version, and so fails. The parameters are corrupted or whatever. So I'm going to give some, hopefully not too complicated, details about how we do capture and replay. So when the Vulkan loader pulls in our layer, we give it back a big table for all the Vulkan functions, which contains what functions we would like to be called. And so one of those, for an example here, is create image view. So if an application calls vk create image view, it actually calls us. Potentially, might actually call us through other layers first, and then there might be other layers downstream. This can get really complicated. But what we do in our function is potential preprocessing. Then we call down chain, and that means call the next level down, which could be a layer or a driver. Then we take the inputs and the outputs for that function, which may or may not have been successful, and encode them into a buffer. What we do with that buffer then is pass it off to the Vulkan capture manager to do something with it. And I've written K-mode track and K-mode write, and these are basically just bit masks that we keep track of. So the actual mode is a concatenation of all these, an OR of all these masks. But if we have track mode, that means we are not yet storing frames to disk. We're just keeping track of state. So we add that state to the state tracker. If we're actually K-mode write, that means we are writing frames to disk. We've already written all our state. And so instead what we're going to do is take the information for this function call, a header tag which says it's compressed function call block, the actual API call ID for vk create image view, and all the parameters, optionally compress it, and then we store that as a record in the capture file. So I guess I am giving more detail, but right. So on the other side, the file processor reads blocks from the file. If it finds one that's a function call block, this is also a bit mask. So this could be function call block or compressed function call block. It knows to call process function call also in file processor. And then what that does is it reads this block of data from the file, potentially decompresses it, figures out if the current decoder can support the API call that's been made, which we have just the Vulkan decoder, so the answer is yes. And then it calls the decoder to do work with that. So the final thing we do is in the Vulkan replay consumer, we actually take all this parameters from this buffer and decode the real parameters for vk create image view, which is like the device handle, the create info, the image and view that you want to use to create this composite image view, and then actually calls Vulkan with those things. And I want to mention, we don't store the actual handles that Vulkan passes back to us on capture. What we store is an incrementing index, basically a small integer, which could get bigger, I guess, in case of very large apps. But since we store there's no point in storing the handles or the memory pointers in capture because those will be different on replay. So we store identifiers instead and then remap those when we play them back. Right, got a little bit ahead of myself on the slide. So this is what does that work. Not drawn here is a lot of the stuff that I talked about earlier. There's a fair amount of complexity in here to do things like the virtual swap chain work, to remap memory. We try and keep those encapsulated in classes as much as possible, of course. And so those of you who've used GFXReconstruct have known, I think, possibly that it's been out for several years. A lot like other open source projects, you could download it and try it, but there haven't been guarantees about the file format or the version. So we're closing on 1.0. And so some tasks left to be done are to version the file format, make sure that that's the numbers documented, and that we have some clarity on backward compatibility. And of course, we accept issues and PRs on the GitHub repo. So how much time we have available to review those and do stuff with those depends a little bit on how much of the workload we have. We're a software consultancy, but we try to spend time on those. And so we're going to do a pass on identifying and tackling anything that we think really needs to be resolved for 1.0. And if you look at the issues list, there are a handful of those that are a big deal. And so I guess I'll try a demo. So we'll see if we can make this work. Okay, open on the wrong screen. So I'm running Vulkan configurator, which I think is the easiest way to do this. Yeah, and of course it's going to be really tiny on the screen. But when you run this, you get a series of configurations that you can run. These are layer configurations. The whole point of this tool is to set up layers, provide the settings for those layers, and then run your app. And so in this case, I've got frame capture. Here's my layer for GFXReconstruct. Got a bunch of settings. I'm just going to set it to capture everything that it does. I've got VK Cube set up here. And I launch it and it shows up there. Good. Okay, wait for it to run for a second. It's interesting how, depending on how you have HDMI set up, it might run slower. This is slower than I expected, but this is not about performance. This is about capturing the data. And so you can see down here, trying to do this without my glasses up close. This is the important part that's the output from this layer, which is the file name. Oh, it's probably a mistake. One thing the VK config does is it changes all the layer settings. So if you're going to mess with it, the best, if you're going to be running applications and doing something different, the best way to deal with that is to just cancel. So now I should be able to gfxrecon.py replay. The script is basically kind of like Git or other tools where you have subtools. They're actually called gfxrecon-replay in the tool chain, but you can provide a sub command here, and then we provide the capture name. And there it is. It's actually replaying all the Vulkan calls that were captured for VKCube. And it plays it till it's done. You can ask it for info. So some whoops, actually pretty low. Okay. Notable bits here are the compression format is LZ4. You can actually make an uncompressed trace, but of course that's quite large. Total number of frames, 672. And then some more information like this is the data that was provided to create instance about the application. And for my next trick, I'm going to put my microphone down. I'm actually going to clone a repo that I have here and build it, and then run the new tool to convert to ASCII and show you what that looks like. So hopefully I can do that in just a moment. If I'm lucky, I have most of the stuff in my history, so I can keep the microphone in my hand and just push up arrow. Nope, not lucky. Yeah, there it is. Okay. So and then somewhere in here I've got a make command. It is a pretty beefy laptop, so this may not be how quickly it builds for you, but in general, it's quite fast to build on Linux, or using Gradle for Android or on Windows. And I think while that's happening, I'd like to talk about my favorite project. It takes about a minute to build that. And so many of you know that I am very interested in old technology. And so one of the more fun things I like to do is to run things where they're not supposed to run. Not done building yet. Okay. And this slide makes it sound like I know what I'm talking about, which is the really great part about it. But I've actually done some CPM work. That's how old I am. And one thing I've kind of always wanted to do was to run an old 8-bit CPU in a shader. So I've always thought that would be a little bit weird to get the output, but maybe an interesting thing would be to run like every possible combination of keystrokes or something. Okay, so now it's done building. Good. Okay, so here's my command line. Let's get this up on the screen a little bit. Stick out my crazy slide back there. Okay, so there's what I built running VKCube. So it's capturing now. Hit escape because we don't want to do 5 minutes of those. And then replay that. Maybe. Well, since you've already seen it run in replay, what I'm going to do is just convert to text and show you what that looks like. Okay, so this looks pretty horrible. It's JSON lines, which means every command is a JSON record on one line. And the reason we did that and not just like a huge JSON record is that these captures can be gigabytes. And when you convert them to ASCII, they're also gigabytes. And so you could easily choke a JSON parser. So instead we do it line by line. So you can do things like grep, use the Unix text processing tools or whatever you'd like, and just read it record by record. But what you can do with smaller traces is run it through JQ, which is a JSON processing tool. And so then you get something which is a little bit prettier. Yeah, there we go. We have a header which includes some information about the file. And then of course here's your first function, which is create instance. And I was talking to someone earlier about debugging traces, debugging Vulkan code with an ASCII dump. And so one of the examples that I have here is you want to do a bind memory. You want to find out what happened there. So here's, now, yeah, one-handed. Is it bind image memory? Thank you. You know what? I bet I have it in my history, so I'm just going to go find it. There we go. Okay, so what you see here is this record is indexes the ordinal of the function in the capture. So it's the 50th function that was called. The name is vk bind memory, image memory. It succeeded, and the important things here that I want to point out are image and memory are these handle IDs. So these are not the original handles, but since we're inside the capture, what I can do is if I want to know more about the image that was bound here, I can search for image 23 as an output. Yeah, I'm gonna type this wrong again with my left hand now. And let regex solve some problems for me. Okay, so here's actual p image was created in this function here, which is create image. That was just a little bit earlier, index 47, and you can see it's a 16-bit depth format buffer, 500 by 500. So this is the depth format for the screen. So this is how you can sort of jump back and forth through the ASCII stream with this. Now, if I could just find my mouse. Nope. Okay. So thanks. You can check out the GitHub repo for the source. And if you have any questions, you can send me an email. If you have any questions offline, but I can take them now as well.
Hello.
Hello.
So you said you have a page guard version. On Linux, do you use exception for that, or do you use mnsoft 30?
The question is, how does PageGuard work on Linux? I don't actually know the details. I know we set up a signal handler. So I think we're touching the actual, like mprotect on the page. Yeah.
Print that JSON output, kind of like the API dump layer does, or maybe it's just not just the API dump layer.
Right. The question is, would it be better to pretty print the JSON output or do something like API dump? Because API dump, who's used API dump and looked at the output of that? Okay. So API dump produces very verbose output, which is extremely useful. We sort of tried to strike a middle ground between producing output that could be debugged and not dumping a really huge file. So we, in particular, a non-goal is replaying or from this dump. So I think what API dump gives you is really close to something you could play back. Like you could reassemble that into a file if you had a sophisticated Python script. So one thing we can do is we can turn API dump into this format for testing. We could probably do the reverse. It's not a very complicated piece of Python, so I'll take that as.
The JSON has all the same information that an API dump would have.
It's very similar. API dump outputs all the types for all the objects, which is super helpful, but that just means that the types are repeated over and over again. And so we chose in this case to not output the type because the type is very well represented in the spec and in the header. So it's missing that. And I think that might be a little difficult to go back to from this format. But the idea here was to make something that you could look through and dump out and say, oh, that's what I expect, or that's not what I expect. And so hopefully it does that, but it's fairly new. So this is an opportunity to say, this doesn't do what we want. It would really be great if it did this other thing instead. Yes. Okay. Could you repeat? Yeah. Right. The question is, do we plan to reconstruct the threading behavior as well? So, because right now I think we're single threaded, we just play back everything as it came to us. The answer is yes. It's in our roadmap. You know, you can't make super hard schedules sometimes, but it is actually pretty high on our priority list to make separate threads and make them behave that way. As you can imagine, there's just a little bit of design that has to go into doing that right. So. Right. The statement is that perhaps before timeline some before you might have gotten correct behavior no matter what you do. I'm not sure about that, but afterwards, yeah, we haven't looked at it too much, but I agree, it's a big deal.
We also have a question from online audience. This is very useful. What's the catch?
What's the catch? This seems very useful. What's the catch? Good question. I mean, yeah, you want me to talk about what's wrong with the thing? I mean, yeah, I don't know if there's anything that jumps to mind. It is a replay of the Vulkan commands, so it doesn't include things like system calls. There are lots of cases in Vulkan where you take memory from another API and you hook it in through. Let's see, there's struct chains you can add to allocate memory to say, I'd actually like to use this Android buffer over here. And we do the best we can to say, well, we know that there was that linkage, so we'll create a dummy version of that, but we don't know anything about how that was made in the Android app. We don't catch those commands. So that's a limitation. Sort of by design, we don't catch all the other stuff that's going around the application.
Hello. So why do you use unique, like, monotonically increasing IDs for each object instead of just like dumping the pointer value? Because when I tried to do something similar in DPD12 API trace, a lot of overhead seems to come from taking the pointer and then looking at the monotonic ID when you could just do that on the replay side and not have the performance penalty on the capture side.
Yeah, so the question is, why do that monotonically increasing ID on capture, and then we also remap on replay, right? So I guess we could store the handle IDs, the handles directly in the capture file. We'd still have to remap them on replay, right? But I'm going to be totally honest with you. Some of the design was by someone else who's left the company. So I usually trust his design instincts. So I'm sure there's a good reason, but I don't know what it is. So what I do know is that you can reuse a handle in Vulkan. So at any given place in the capture, if you see a handle, you don't know whether that is the same handle that you saw earlier or whether it's been deleted and recreated and you actually have a new object. So if we do the incrementing integer handles, you know it's a new thing. So there's that. Yes. So if you have all the context in between, you know it was destroyed. But if you don't have that, if you just have like pulled out pieces, then you don't have to keep track of that. That's true. So yeah, there's some design decisions which may or may not have been differently in the sands of lost to the sands of time.
Whenever you have, I mean, some games like to use the GPU to compute more I don't know how the waves of the sea of the move using something like feedback or something like this. And I think that small errors tend to grow with time. As in, like, let's say, okay.
Okay, so the question is about basically taking outputs of like shaders or transform feedback and then using them as inputs to another stage later, right?
I'm getting there, but yeah, okay. So, with the context of
in the context of trimming.
Is like, let's say the driver rendering checks. So we want to do some CI and verify that the game output doesn't change. So this is the context. So when we run the trace, we currently run it from the beginning to the end. So that means that essentially it's multiple minutes of let's say gameplay. And if some object, the location is even like updated every frame, then small errors are found, and the position at the time while we actually take a screenshot can be very different depending on the every time you would run it, you would get it at a different position.
Every time you run like the shader to do updates of the inputs, outputs. Every time you run the trace again. Okay, so you're saying that you run the trace, you have certain values on the screen. You run the trace again, you have different values. If that was the case with GFXReconstruct, I would consider that a bug.
Okay. So in order to remove these issues, trimming is great. That would be great because then we would be able to, we would not have these compounding errors that much because then we would just have the data that we at the time of the trace.
So the question is about these compounding errors. I'm not sure where those compounding errors would come from because presumably you initialize everything at the beginning of the capture. But if there was something where somehow, so the way trimming works for us is we collect up all the state, and I believe before we do a draw for the first time inside the trimmed range, we save off all the current state. So whatever was the state accumulated in capture, to that point, that's saved.
Yeah, so that's
Yeah.
So the rest of my question is, would it be possible one trace that would be having multiple, because when you trim right now, you only have one frame per trace file.
Oh, you can have multiple frames.
You can
Yeah,
now.
yeah.
Okay, so that's what we're
Yeah.
Okay, so you can do this, and so that would be a way to remove the
Yeah. Well, you can, well, I mean, you can do this much. You can say like frame, you know, like you want frame 100 through 200, and then you want frames 200 through 300, and it'll produce 2 capture files that represent those. Yeah, I'm not sure quite the way around that, really. I mean, like, you want something where a single file capture can replay and draw only frames 100 to 200, and then only frames 300 to 400.
then frame 33, then frame 44, and if the architecture is all handled or whatever can keep between, that would be great.
I think we should probably talk about that offline. I'm not sure that that would be that difficult given the way we do things in the capture file, but I'm not sure I understand the use case, so we should probably talk about it offline.
Hello again. I just had a look at the code, and yeah, it just seems to be like a typical segfault handler.
Yeah.
Is there anything preventing you from using MM-Soft30? Because when I did it for easy development traffic, which obviously was too wide and whatever, we needed like a flag. We needed an extra kernel function to be able to reset the mappings. Is that what is preventing you as well from using MM-Soft30? Because the performance uplift from capture from using that as opposed to segfault handling was pretty extreme.
So right, the question is reaching technical detail that's beyond my limit. So, which is about how you do the protection on pages for PageGuard. So again, something we can talk about offline. Our performance during capture is relatively good. So that is right now, performance in capture is not an urgent thing that we're trying to address, but we can always take suggestions. So we actually have a lot of work going on right now, especially in terms of Android and getting PageGuard improved. So we should talk offline. Yeah.
As far as I know, it's possible to just replay a specific frame. But is it possible to replay the capture up to a certain command?
No. The question is, can you replay up to a certain command? The answer is not yet. So so far the design has been pretty heavily based on frame trimming, but it is in our list. The high priority item is to do at least 2 queue submissions, and then maybe draw after that. But yeah, I know that that's a big deal too. It's just you know, more state has to be tracked. Oh. Any more online or any more questions? Great. No one wants to talk about what would have happened if the Atari 2600 had a Z80 in it? No? Okay. Great. Thank you very much.
All right. Hello. So, I'm here to talk about compute-only GPU or implementing the graphics pipeline on top of compute. My name is Erik. I work for Collabora, and yeah, I'm a graphics engineer in the team there, working mostly on Mesa and related technologies. First, a disclaimer. This talk does not represent any active project I'm working on. This is more kind of an outline of how any future projects along these lines could be done if someone decides to do it. That doesn't mean that I'm not interested in working on such a project, but it's a huge undertaking to take upon yourself. So yeah, so I'm gonna then do some background for what I'm talking about here. So where we are today, the GPU in a computer system is basically no longer optional. It's something you need to boot useful systems, and large resolutions and power usage, memory bandwidth, those kinds of things. Means that often software rasterizing on the CPU is not really a viable option either. But on the other hand, GPUs are large, complicated things. They contain a lot of machinery. They are kind of scary from a security point of view because they need to be bus masters and can kind of read and write. They have free access to the memory that's visible to them, and can go rogue and kind of do bad stuff if programmed incorrectly. They're also developed largely closed and something that most people can't have a look at what's happening. And that's, I mean, that's I think natural from the business end of things, but it would be better if we could have something that could replace this for some kind of systems. Yeah, and there's a few unfortunate effects that comes from this. The obvious security concerns. Hardware research, I think, is kind of interesting. It's really hard to do proper hardware, like GPU rendering research, without having access to a working, modifiable system. And then finally, it's really, really hard for a new player to enter into the market. Even if they're not even like a commercial player, it's well, especially I guess if they're not a commercial player. So I think we need to have an open source GPU. The ecosystem kind of needs that to pair with this new fancy open CPUs we have, and to build kind of critical kind of systems, stuff like that. I'm not proposing making something that competes against the existing vendors. I think that's a fool's errand. They will kind of all, at least in the foreseeable future, be far ahead with more features, cheaper, ready products that you can buy, stuff like that. So I think competing, for instance, on the desktop stuff is a bit of a stretch. So instead, doing something that targets research, prototyping, and niche use cases. And for instance, one niche use case I can think of is if someone needs to make a camera chip, they need a lot of compute power to do image processing, but maybe not so much graphics, but they need kind of to do some graphics as well. So maybe for them, it's an okay trade-off to not or to use to software rasterizing in the compute units. Yeah, and making a new GPU is a very, very big task. The hardware development costs are pretty high. It takes a lot longer to build something in hardware than it does to do it in software. And if you make a mistake, you have a really, really bad time. You need to lock down your design and tape out stuff, and yeah, spend ridiculous amount of time in software working around bugs if you end up shipping with some. Yeah. So it would be great to shift more of the stuff in a new implementation into software, and doing that in a way, I think, where we just don't end up building like yet another software rasterizer that's just a little bit accelerated with some vector instructions, which some projects are trying to do. Yeah, so here's just a very dumbed down version of the graphics pipeline, or listing some of the stuff that's happening inside of a GPU. I obviously don't have space on a slide to list it all. And all of these, like some of these would kind of still have to exist in some way, but at least these ones, I think, are things that could to some degree be, or could be done in software. Yeah, as a first approximation to this. The programmable stages would, of course, just be lowered into a compute shader and be run as kind of, yeah, on that unit. So let's talk about Laraby. That's, I think, a lot of people thinking about when about what I'm saying here, because Intel tried to do this back in 2008. They announced the project. It was an x86 based GPU architecture that did most fixed function operations in software. It was targeted toward the same markets as NVIDIA and AMD, to some degree at least, back in the days. And it was immediately very popular in academia. So the SIG-graphs and stuff around those days had tons of papers on kind of how people could do stuff on Laraby. And then a year after, a little bit more, the project got cancelled. In the end, it ended up shipping in some version with a Xeon Phi, but that's targeting quite different markets than what they were doing originally, mostly high-performance computing stuff. So what went wrong with Laraby? I think there's a lot of things that went wrong, to be honest, but I will focus on two things here, which I personally believe are the most fundamental things. One is that x86 is not a particularly good choice for building a GPU architecture on top of. It's like the benefits you get from using x86 just don't benefit you in a GPU. So one thing that like Intel focused a lot on in their marketing about how you could run the same code on the CPU and the GPU, and that's just not true. First of all, because the Laraby CPUs were Pentium CPUs from ancient days already at that point. Didn't support most, of the extensions they've added and stuff like that. So maybe you could run, in theory, the compute kernels on your CPU, but yeah. And then I think much more important is that what makes a good CPU ISA is very different from what makes a good GPU ISA. And there's, again, multiple things that kind of works against each other here. But one of the kind of ones I like to talk about here is that kind of like pipeline depth. A GPU can benefit a lot from a very long pipeline, and using that to mask memory latency. Whereas a CPU, if you do that, you have a very, very bad time because you need to be able to respond to stuff like IRQs quickly. So having a long IRQ latency is not great. So yeah, it's I think that was a mistake, but it wasn't like they had very good options back then, because back then there was no compute shaders. There were no like CUDA had just been announced, and that was kind of the closest to having something that could be used. And yeah, Intel will obviously not do that. And then secondly, which is also a big deal, is that they were unable to scale up to the competition. What they announced on paper back then was already kind of behind as they announced it, and they were far from shipping. So yeah, it takes a really long time to ship a GPU, and the scaling did not go as well as they were hoping. And yeah, also part of this scaling problem is that the software, the texture mapping was done entirely in software, which is yeah, not good. That's just never going to work well. So what has changed since Larrabee? So I think one thing is that GPUs are everywhere now. Like I said in the beginning, it's a requirement everywhere. You have them for other reasons than rasterization in a lot of places. And that gives us a bigger spectrum of requirements, and it allows us kind of more flexibility in how we're doing this. And then secondly, the GPUs are much more generalized now, and in that I mean specifically we have compute shaders. Compute shaders is I believe a much better target for something like this. And then also means that we can do this without targeting a single architecture directly. So we can do a generic implementation that can run on any compute shader. And yeah, we can start doing that today because we don't need a stripped down GPU just to be able to do these things. And yeah, I'm obviously not the first person to think of this. There's been other approaches similar to this. None going kind of as generalized as I'm proposing here, but yeah. So I'm dividing this talk a bit into the software and the hardware side, and the software side, because I'm a software developer, is obviously going to be much more significant than the hardware side. But yeah, so previous implementations, other people who thought of this, there's kind of sort of chronological here. There's a project called FreePipe that did an implementation of the graphics pipeline on top of CUDA. Then there's a paper from NVIDIA from a research project they did called High Performance Software Rasterization on the GPUs, or on GPUs. And then more recently, there's been some emulator works for older games consoles where people have been trying to do emulate stuff like Nintendo 64 graphics quirks by doing the whole rasterizer as a compute kernel. And yeah, finally we have in Unreal Engine 5, I think is the version now. There's Nanite, which does software rasterizing in compute shaders as part of their production solution. Right, so what I'm proposing to do is to kind of aim high but start slow. So focus on, or like target, like the goal should be to reach like full feature parity with modern APIs. I'm only mentioning Vulkan here because Zink exists, ding ding ding. But I think at first, like kind of an OpenGL ES 2.0 like feature set is more viable, and then kind of go from there. But for some technical reasons, we're probably going to need a more complete ISA than that. Stuff like integer operations to do robust rasterization, things like that. This could be implemented as a Vulkan layer on top of a compute-only Vulkan device. So you would have an extension that you would inject into device enumeration. So a device that is out of spec could appear if you ask for it to do. Yeah, so let's talk about the texture mapping, because that was kind of that's a very important thing here. And computer shaders can do texture mapping, so there's I think
that should be a requirement from day one. It's just not gonna. Texture mapping has so many little operations that needs to be done and kind of be done in a very careful way. There's a lot of details in there to get right, and to optimize for that is just, it is not fun. And if we look at, for instance, LLVM pipe, there's a lot of traps in there. There's a lot of flags to flip on and off to get conformed behavior or to get fast behavior and things like that. And I think it's a very important thing also to do something along the lines of VKNV compute shader derivatives, so we don't have to deal with a manual LOD calculation. We can lower textups to TXG and use shared memory and subgroup operations or whatnot, but it's quite a lot of work, and there's quite a lot of lowering that would be needed for that. Which So one approach to implementing something like this is as a mega kernel. So basically take the whole graphics pipeline and compile that down into a big compute shader that loops over so launches grids for the entire, like a grid for the entire screen, and input assemble up to n primitives, and then do write to shared memory, do a barrier, and then switch to vertex shading over for the same lanes, and then switch back to primitives with the barriers and stuff, and kind of go back and forth. The problem with that is that this kind of number n needs to be constant, and you end up with lots of empty lanes. So a better approach is something called a wavefront formulation. This is inspired by, again, an NVIDIA paper called Mega Kernels Considered Harmful, about wavefront path tracing on GPUs. So the idea about wavefront formulation is to have many smaller queues with where you fill them up with operations, and they kind of go back and forth between doing, like, iterating over what needs to be done. With that approach, you get much better occupancy. You get rid of a lot of little details. You can compile your pipelines in a much healthier way, because you can kind of do like states dependent blocks that don't change the entire program every time you change some state. Like a division here could be something like the input assembler, the vertex processing, the primitive setup, hierarchical rasterization, and then finally fragment processing in one bigger kernel. So some of the stuff that needs to, so I just want to say that I'm focusing mostly on the rasterization bits here. The rest of the graphics pipeline is not that interesting. I think it's kind of obvious how to translate a lot of that stuff. So the primitive setup kernel would do basically set up edge functions per, like 3 or 4 edge functions per primitive. Triangles have 3, rectangular lines have 4, anything else, something in between, depending a bit on what you're doing. So we'll set up that bounding box and store phase winding, and then do clipping or culling. For clipping and culling, the options are to do a clipless rasterizer. That's going to be needed for doing depth clamping anyway. And then discard things that are outside of the W range. Or it can do geometric clipping, and I think it's going to be a bit of a benchmarking work to figure out which is better in which cases and stuff like that. But for rasterization, basically what you want to do is you want to evaluate those edge functions per tile. By that I mean, for is basically doing hierarchical rasterization, and you can, for each tile, you can pick 2 corners of the tile that are the extreme points for each edge function, and you can do that by just adjusting the value, like the constant bit of the edge function, and then you can test if a tile is fully inside or fully outside of that tile with just to evaluate those. So it's hierarchical rasterization is actually fairly cheap compared to per fragment, where you need to check all of them for everything. So you do that down to 2x2 and then schedule 2x2 pixel groups for fragment shading. For those who don't already know, that's standard for GPUs to do this. You want to shade 2x2 groups of pixels so you can do derivatives, and most GPUs do it even when you don't do any derivatives, just because it's easier with the same kind of flow of data all of the time. Yeah, and then per fragment, you get into like the kernel that does the per fragment stuff. You can evaluate the edge functions for tiles that were not completely inside. Tiles that were completely outside, you've already discarded. This needs to be integer math, otherwise you're never going to get it robust. So, but yeah, and then at the end of the fragment shader, you mask out the pixels from the pixel group that fail because of coverage. You can do more. You can optimize. You can terminate them a bit earlier based on some shader analysis, but it's not as easy as it sounds. Yeah, and the pixel shading itself is kind of evaluating the depth and barycentric functions. The Z needs to be linearly interpolated, so that's like a little bit different than the rest of the barycentrics. And then the attributes need either perspective correct or linear barycentric functions setup. Then you perform early fragment tests, execute the fragment shader, which would just be kind of inlined into the same program. And then in the end, you run the fixed function pixel operations, so the late pixel fragment tests, blending, dithering, if you're bothering with that, these kinds of things. So how would something like this perform? Sorry for stuffing a bunch of different things in here. So just to summarize what this slide says a bit, it's kind of all over the map with the prior art solutions. They claim very different numbers. Some of them good, some of them bad. Some of them correct the other ones and tell us that even though they claim to be good, they're actually kind of bad. But I think the kind of most relevant is the Lyude et al. Paper. It claims between 12 and 50% performance of native rendering. That sounds pretty bad, but this is in very, very targeted benchmarks where they basically are trying to look for make the rasterization part as big a bottleneck as possible. So I wish that paper, which is kind of the closest to what I'm proposing here, would have provided real-world numbers. And I have not done enough work to be able to provide real-world numbers myself. But I believe that that's a very conservative estimate. That it's more probably going to look closer to 50% to maybe 90% or something like that, depending a bit on what you do. Yeah, and Nanite is a bit of an odd case because that one actually ends up beating the rasterizer in a lot of cases. Which I don't think we can really expect with something that's actually conformant, because that's the benefit of Nanite. It doesn't need to care about OpenGL conformancy or Vulkan or whatever. So the Nanite rasterizer, as far as I understand, I don't have the source code, so I can't read it. But as far as I understand, it doesn't do tie-breaking rules properly because it doesn't need to. It does opaque geometry. It can tolerate a little bit of overshading, and that's very little overshading that you actually end up getting for not being spec conformant. It also I believe, does its Z interpolation in perspective, like a perspective corrected, and that's okay for them because they only draw small triangles. They don't do big triangles, and then the difference will not be very big. Yeah, and they can do stuff like culling instead of clipping, because the small triangles are never gonna intersect both the screen borders and the guard band. So yeah, all of these kind of adds up and removes quite a bit of instructions from the inner loop. So I don't think beating Nanite is realistic. Yeah, so as I said, prior art doesn't give very clear answers. Yeah, it's gonna depend on which fixed function operation you do. It's gonna depend on how much shader complexity you have. But I think there's very little reason to expect the shader evaluation itself to have any noticeable difference. So the rasterization is gonna be the bottleneck comparing to GPU rendering here. So the hardware side, again, I'm not a hardware engineer, so I'm like, this is a little bit outside of my field, but I've looked for what exists out there. So we have I found one project that's called VeryGPU. That's targeting machine learning workloads. They intend to support HIP and maybe Cycle or CUDA. I mean, we're doing software, so we can probably change that. It's based on RISC-V, but they're not fanatic about it. And by that, they write in their documentation that they're very clear that they don't intend to have ISA compatibility. They're just kind of using this as a starting point, and they're breaking with RISC-V when they need to. It's largely incomplete. It's in somewhat active development, but they are limiting themselves to mostly machine learning kinds of features, which means stuff like small vectors rather than full floating point and things like that. So there's a lot of work that wouldn't have to be done there to make that useful. Then there's also stuff like the RV64X and the LibreSoc things. I think they repeat some of the mistakes of Larrabee of trying to repurpose a CPU ISA. They're kind of built on the assumption that like encoding vectorization is the problem here, but hiding latency is actually what you really want to be doing. So these kind of start looking more like just making a software rasterizer perform faster, which could be nice in itself, but it's not what I'm looking for here. So that's unlikely to be useful for this. And then there's one that I think is pretty interesting. It's called Meow GPU. It's a compute-only GPU based on the AMD Southern Island documentation. So it implements the ISA of AMD Southern Island. Sadly, development seems to have ceased around 2017, but they claim that their compute units are complete. They're obviously missing the rest of the GPU around this. So again, lots more work to be done here, but I think this could be a good starting point for someone who wants to dig on this end. So yeah, that's most of the meat here. So my conclusions here are just, there's a lot of work to be done if we want to do this, but overall it seems viable to me. I've also made a very small prototype, but it's not particularly interesting. It's just kind of doing the rasterizer bits, and it's also not doing them in the best performant way. It's kind of doing the first everything into one kernel, and then it ends up reshading the vertices for each local group and stuff like that. Yeah, performance impact is still largely unknown. There's more work needs to be done to know how that actually ends up performing. And yeah, just generally big question marks everywhere. So that's what I have to say. Thank you. Collabora, always hiring. And I was thinking I would just kick off. here's my little toy rasterizer. it's a clipless rasterizer using the kind of edge function stuff that I talked about before, running in a compute shader on top of the Intel stuff. It's of course needs much more work to be like one triangle. It's not so exciting, but at least I have something running. So if someone has any questions, I guess this is the time.
Didn't expect any likely not any significant performance of shader evaluation. At the same time, I totally agree with you. Hiding memory latency is very, very important for GPUs. And one of the main limitations there's a number of registers, especially if you're going to build it on top of a Southern Island State ISA. The concern there, this is more than an open question, I guess, is that when you build anything larger and larger shaders, even if it technically doesn't necessarily lead to your register use, it's going to blow up. Which is going to probably impact your performance of all those.
I'm not quite hearing what you're saying. I'm not quite hearing what you're saying now.
The memory latency hiding is important, but if you build larger and larger shaders, like combining multiple shaders, like your memory, your register usage is likely going to explode one way or another, even if it technically doesn't absolutely need to. So ultimately, getting that overhead to not be that big is going to be a very interesting challenge. It's not actually having huge overhead for data implementation.
Yeah. So for those who didn't hear that, I'm gonna just summarize it quickly. The comment is that register pressure is going to be a problem with an approach like this because you're gluing together or like baking a lot of stuff into the same thing. And yes, that's I think very true. This is again one of those things where you need to see need to have something running to kind of see where like how bad it is. I'm hoping that register pressure, like register won't live too long across different kind of subtasks. But yeah, we will see. I'm also worried about that.
Question from live audience. Have you seen Newsy? Any thoughts on their approach?
Seen
Newsy, and why?
So the question is if I've seen Newsy. I have not. So no. It's a different approach. Yeah, I don't know.
So is this project mainly focused on architectural exploration for, let's say, at a basically like hardware architectural exploration, like more the GPUs using software basically? Is this like basically architectural exploration project that's prior to doing RTO? It's sort of like what the kind of role proposal.
Yeah, so the question is if this is more of architectural exploration before any RTL code is written. And so yeah, all I'm doing is kind of playing around with the idea at this point. I'm not planning on actually going ahead and finishing up this work. But at the same time, I want to stress what I said a bit earlier, is that because this is targeting GPU compute shaders, we can actually do a lot of the work up front. Like it's not the software stuff is not really dependent on hardware being ready yet to at least get some idea of how well it's going to go.
If I were to follow, so basically, to get this thing kind of fully going, funded, you probably need like possibly multiple firms that want some kind of more open hardware IP block to jointly fund this project, right? The early stages, which is more the architectural stuff, and then eventually, you have to realize that there's some kind of silicon IP, right? So you probably need multiple firms to chip in funding, right?
Yeah, so the question was kind of, I guess, how to fund something like this if it would want. Yeah, okay, my laptop is running out of battery. I'm gonna. Yeah, so the question was about funding this, kind of if we need to get multiple teams together or something like that. I have not thought about funding myself. I would say an open source GPU, which I really hope will happen, is something that would need funding. There are some projects existing, mostly driven by universities. So I think if you're talking about the hardware side, then yeah, that would probably need some sort of funding. I'm hoping that academia would be the right thing to fund that, or like having students work on it, stuff like that. But yeah, alternatively, if some company needs like wants to make their own GPU without a rasterizer, collaborate with a consultancy, we can help out. Yeah, and my also to be clear about that, my preference for the rasterizer bit here would be to do this as part of Mesa, but that's kind of because that's where my feet belong most of the time.
Which compute shader API are you targeting? What are the trade-offs or the features you're using that would happen?
Right, so the question is which compute shader API I'm targeting, and if there's any features missing that would help, I guess. So right now, like the prototype I'm running here is just a Vulkan application, so using GL slang to compile the shaders using Vulkan compute. I don't think that's set in stone. I'm not, like, I proposed building this as a Vulkan layer, so that would be Vulkan to Vulkan. I'm not sure that's the right solution. Maybe someone will want to have an OpenCL driver instead. Yeah, there's some open questions in the layering there. Like if you want to, if we want to do Rusticl on top of Vulkan on top of this, and then having to go down to OpenCL again would, of course, be crazy. So yeah, my gut feeling is Vulkan compute is the right target, but I'm not sure.
One last thing, so more comment than a question. The failing of Laravel is fixed function hardware is a lot and power efficient. Doing it in software can never compete.
Yes, that was a common, I guess, repeating my second point about the failings of Laravel. Yes, Laravel did too much in software. I should probably have listed that as the reason one and the ISA as reason two, but I just love to, like, whenever I see someone trying to do an open source GPU and using a CPU ISA, it's a little part of me dies, so I wanted to kind of mention that first.
So going back to your sort of performance comparison slide, you mentioned the nanite stuff as a comparison point, and you listed a bunch of reasons, but one of the things that you kind of didn't list there is the fact that nanite completely removes all ordering problems.
Yeah.
It doesn't deal with blending, it doesn't deal with transfer feedback, it doesn't deal with anything that requires equipment order.
Yeah.
And that seems to be something that you're not just going to wave your hands and solve with computer. So I'm curious if you have any ideas on that, or if it's just something that you're leaving to later.
This is something I leave to later. I like to kind of, I like to do things simple first and kind of deal with the problems later. Something I guess Mike knows everything about and hate me for a little bit. But I have not thought much about that. But that's certainly stuff that would need to be thought about properly. Yeah, and I guess that's time, right? Yeah. All right. Thank you.
All right. Hi, everyone. My name is Lyude Paul, and I am the current secretary of X.Org. This is going to be a presentation about where the X.Org Foundation is at and what's new. But first, huge thanks to CodeWeavers for hosting this conference, and special thanks to everyone who helped to run this year's XDC. Without your help, we definitely wouldn't be here, so it's greatly appreciated. Thank you. So on the topic of sponsors, we had about 11 sponsors this year. 4 travel grants were provided to students. Thanks, Emma, for doing all of the invoicing, and thank you, Daniel Vetter, for doing all of the sponsor hunting. We had about 30 accepted talks. We had 26 full slot talks received, 8 half slot talks received, 4 lightning talks, and 1 workshop. So a big thanks to everyone on the papers committee who helped to do all the paper reviewing for that. And so XDC 2023, where is it going to be? We're not quite sure yet. You're welcome to submit an RFP if you'd like to help host XDC 2023. We're looking primarily for places in Europe, but you know, if you want to host it all, I would definitely recommend putting in an RFP because we might be able to fit you in for the next year. And of course, it is, as you could tell, since we're here physically, it's very unlikely to be virtual this year. So X.Org free desktop infrastructure updates. Not a whole ton going on here. Things have mostly stabilized. We definitely could still use new volunteers. And yeah, things tend to be working pretty well overall there. So of course, the free desktop code of conduct transparency report. Excluding spam bots this year, we had 1 complaint of recurring behavior resulting in a ban, and 2 formal complaints just resolved with warnings. We did get a lot of spam bots though, so we did have to put a little bit of effort into figuring out some extra ways to mitigate that. But so far, we seem to be doing a pretty good job of that. So GSOC, EVOC, and Outreachy, we're back in Google Summer of Code finally. For those who aren't aware, last year we kind of had to drop out of it because of some of the project limitations, which weren't really great for a lot of the projects that we would have students working on since there wasn't really enough time given. This year, we both were able to find new volunteers to actually help out with running it, which we were also having trouble with. And Google also changed a lot of the rules around how that works so that now we have 2 classifications for short projects and for long projects, which works perfectly fine for us. So as a result, we were able to get free students in, and every single one passed and was able to attend this conference. So congratulations to the students who passed, and thanks for coming to our community. And a big thank you to the people who really helped to step up and make this possible, Trevor Warner and Rodrigo. I don't want to mispronounce your last name, so I'm just going to leave it at that. Outreachy. This is the one thing we'd like to get back involved in, or get involved in again, but we both haven't really had that many volunteers. But yeah, if you would be interested in doing this and you have any projects that you'd like people to work on, feel free to contact me or anyone on the board. So this next slide, I embarrassingly forgot to type. But luckily I know most of this off the top of my head. We're currently looking at having the Software Freedom Conservancy be the new parent organization. As X.Org has been growing bigger, the needs of X.Org have also been increasing, and it's getting to a point where we kind of want to have a larger foundation be able to help support us and be able to also help with various organizational tasks that we have up until now been doing ourselves. And yeah, of course, none of this is finalized yet. All of this is going to be going through a public member vote before we make any final decisions on anything. But yeah, we're hoping to get a lot out of this, and we're hoping to help get a lot of possibly infrastructure help. We don't really know what's going to happen with that yet, but yeah. So that just leaves the foundation. You can be a member. If you're in this room, you probably are able to be a member. There's lots of benefits to members. You can vote. You get bragging rights. You'll be the cool kid in the room who can say, I'm an X.Org member. You get access to specifications such as the DisplayPort specification and many other specifications available through Vesa. We also offer Khronos conformance. We've helped a number of drivers actually get certified by Khronos, and we have an agreement set up with them to help make that easier for everyone. And of course, as I said, all the cool kids are doing it. Don't be the odd one left out. And oh yeah, of course, anyone who qualifies is probably in this room. So you can go to members.x.org and sign up. So do we have any questions?
So you mentioned switching from the SPI to the SFC, if I understand correctly, and we currently have a lot of member benefits, as you say, like specifications and conformance are anytime taken into account to fall. So switch those over, or is that going to be a giant mess?
Could you repeat that last part?
So, like, we have access to specifications and we can do like conformance with Khronos and stuff, and like, is that also, are there already plans on how to move that over? Is that likely going to be a giant mess to get those agreements agreed on this like a new parent organization?
So, of course, we still have to have the lawyers actually. Pardon? Oh, yes. So the question was regarding the specification access and the Khronos conformance, whether or not there'd be any issues with us moving that over to SFC. So, I mean, for us, that's a pretty big deal breaker. As far as we can tell so far, we still have to have a lawyer actually look at it, but so far there's not really any concerning signs that that's going to be an issue. So it should be pretty much good, but we will figure out in the future. We are pretty optimistic about this, though. All right. I guess that's it. Thanks for having me, everyone.
Okay, sorry for the delay. So I will now do a summary of the bare metal CI workshop that happened about 2 days ago. Oh no, yesterday. Feels like 2 days ago. So my name is Martin Roukala. I'm a Valve contractor, and we had quite a few people in coming to the CI workshop. So we started by just talking about what are the different CI farms that are available for open source projects. So Collabora has something that is GitLab based, and it's used for Mesa or DRM testing. And it has quite a lot of Chromebooks there and other devices, but mostly Chromebooks as far as I know. Then there's Igalia, who has, again, GitLab based testing for Mesa on Raspberry Pis. Intel, which came like much earlier, but like these two systems, there's one for Mesa that is invitation based, or like unless you're working for Intel, it's invitation based, and you can do pre-merge testing there. So you push your tree and you get results. Then there is the i915 and IGT CI system, which is based on emails. So you just send your patch series to a certain mailing list, and then you get the results. LunarG has something that is GitHub based for testing for GFXReconstruct. Qualcomm has GitLab-based kernel testing on their devices, and Valve and Igalia also are using GitLab-based testing for Mesa and DXVK on AMD GPUs. And then there's potential newcomers that would be AMD, who would like to have a mailing list-based IGT / display testing. And Imagination Technology, who's also wanting to go into GitLab-based Power VR testing for Mesa. So quite a few interested parties. So here are the general topics of conversation that we had. So there was the topic of how do we better integrate the test farms with GitLab. So there are some issues, for instance, so if developers are trying to run their tests or do some pre-merge testing, potentially if too many of them are actually making testing at the same time, it could prevent merging in Mesa, which is potentially problematic. So it's possible to DDoS. So we're going to talk about this. Then we would need to simplify the use of bare metal CI. Then also we were talking about test suites. So something that would be for trace-based testing and IGT result processing. Making it easier to set up new CI farms so that we would have more actors. And on Mesa CI, reducing development complexity and easing local reproducibility of the builds and run environment. So for GitLab integration, I'm going to try to be very fast. GitLab can prioritize what is project critical job or a developer that just wants to test their code. And so that means that we need to either prevent developers from using the bare metal runners, or we need to add support for job prioritization in GitLab so that every job from Marge is always the next one that is going to be picked and not the ones from random developers. Another issue that we can have is, that running on bare metal runners is different than running on the cloud. So you need two different code paths, and it makes it, depending on the runner that you want to use, and that's a little silly. We can do better by creating our own executor, and this is something that Collabora has already started, and this is also something that my team has been looking into. Then for the test suites, I don't think we're going to have much time to talk about this, but it's in the slides. We'll get there. I mean, we can talk about it after if you want. Simplifying setting up a new CI farm. I'm going to quote Daniel Stone here. That was a beautiful quote. It can't be that companies need to hire a consulting company to run tests. Yes, that's the situation we are in right now. We need to do better. Along with my team, I've been working on making a turnkey solution for CI farms. It's important for us for other reasons, but then this is something that could be used to replicate our system pretty easily, and with documentation and everything. And I have a blog post series on my blog that that explain like, or if you want to make a CI system, then here are the general considerations and what I would recommend. But it tries to be very broad. Finally, the Mesa CI development workflow. Another quote from Daniel Stone: "We have 12,000 CI jobs per day with expected growth." So that means that there are some trade-offs that need to happen between ease of use and reducing the costs on the infrastructure. So, for instance, the containers cannot be built for every single project or build. So instead, there is like a base container that is made using CI template and then cached, so it's not recreated every time you want to run your pipeline. And that means also that test environments and the different variables that you send, like the environment variables for running the tests, they're not baked into a container, so it makes running the same test environment as CI a little tricky sometimes. And this is something that we're going to try to improve by both documentation and reducing the amount of environment variables that need to be passed around depending on the stage. And okay, that was conclusion. Generally, what we can say is that pretty much every CI system is converging towards GitLab-based testing, which is good. There is more research that needs to be done on how to set up a CI farm and on what would be an acceptance criteria for IGT or trace-based testing. And if you're interested in this topic, please join us on Free Desktop, the channel Free Desktop on OFTC on IRC. And sorry for being over time.
I'm up, right? Yeah, so we had an HDR KMS workshop this morning. I had a bunch of people there. I'm going to try to summarize a little bit. I don't think, the outcomes were terribly concrete, but it was good to get people in the same room talking about sort of, making sure we're avoiding all the stones in the water and, not crashing as we're trying to go through this and make this happen. The first thing I want to call out, Red Hat wants to do this Hackfest for GNOME with a focus on HDR, maybe some other display technologies. If you're interested in HDR stuff and you think you'd want to, participate, talk to Carlos Soriano Sanchez or maybe some of the other Red Hat folks who can connect you. That might happen next year, and maybe at that point, some of the pieces will start coming together. We'll see. We need people to work on stuff like this, though. Right now, there haven't been a ton of people working on HDR, at least in the public, but some have. These are roughly the people that were there. We might have missed some that joined later. But we've had Livio Abhinav. We had remotely Immersion with Simon Sir join Sebastian. Some other people. Laurent Pichard was there as well. I really value his input. So what do we talk about? A few concrete things, like I highlighted the inverse EOTF problem and sort of our preferred ideas. I think if we use that, take an EOTF and ask the driver to do an inverse, we really need somebody to code this and see how this looks in practice. So you'll see a running thread through this. Somebody needs to code and try this and, see if this looks acceptable or workable. And then enumerated transfer functions also work, but they're not a good fit for some compositors. Static versus dynamic block definition. Hardware might look different, and you might, currently in KMS, you have the color processing block sort of statically documented, this comes after this. Do we want to keep the static? Do we need to go make this dynamic? Well, I think, if hardware is sufficiently different, and if compositors have a sufficiently different view of what needs to be done, then maybe this needs to be dynamic on some level. If compositors sort of are doing their color processing the same way, all of them, then maybe it doesn't need to be dynamic. And again, some of the compositor work isn't quite there yet, so maybe we'll still find out. We don't want to overcomplicate things unnecessarily, but this is something to keep an eye on. There's also some ideas for color pipeline arrangement, like for a model to deal with dynamic block stuff. Again, I think to really see how feasible this is, we need somebody, that somebody might be me or somebody else, to try and code something and at least, you know, have an example that shows how this can look like in practice. Descriptive versus prescriptive API. Descriptive meaning we describe what the surface, blending space, and output space are. Prescriptive, we say, do this transform in this order. I think at the kernel API, we do need something that's prescriptive. I've sort of arrived at that a while back, and I haven't heard anything in today's workshop that really contradicts that. One thing to notice that a prescriptive model on the kernel side, it could support a descriptive model at a higher layer. So if you wanted that, there might be ways to abstract that or put that at an upper layer. Which brings me, I'm going to go to this slide right away. A user space library could be such an example. There's lib-liftoff, which is supposed to help for overlay planes, but really nobody is using it yet. I think Sway's starting to pull it in. So again, this could use help, and interested parties could work on this or pull this into compositors and maybe optimize the multi-plane overlay portion of it. Something like that could be used to also abstract some of the color processing decisions away, so we don't have an extensively complicated API at the kernel level, but we can still do interesting things, just keep it all in user space. Again, something to explore, and somebody could code up a sketch and maybe try this out. Use cases, I'll get to this, I guess, almost last, but there's sort of, you know, it was brought up that we need to look at use cases, right? We don't want to support everything under the sun, but we want to look at what's actually needed. And again, compositor work is still happening, Wayland protocol work is still happening. So we don't want to get ahead of ourselves, and we want to see what happens in that space, what compositors need, and use those use cases to kind of dictate what the kernel API is going to look like. And then, again, Hackfest if you're interested. Conclusion, yeah, there is some light at the end of the tunnel. We need user space before KMS. Don't rush KMS unless user space has figured out how to do HDR. Use cases should drive API. Hardware vendor optimizations are kind of important and nice, like that ability. We want an API that gives predictable results. A lot of this is vague again, but I think we could, you know, code and try some of this stuff and see if this actually works out as we're moving forward. So there'll still be a long road, I think, for a KMS API, but things are moving in the right direction, mostly. All right, that's...
I just want to talk about OpenCL support in Mesa, which I cannot take credit for in the slightest bit. This has all been recently Karol's wonderful work with Rusticl, which you should have heard about earlier in the conference. With Rusticl, finally, we have an in-tree solution that requires very little special casing compared to what you need for compute shaders. With patches currently under review. All of the weird, load kernel input stuff is gone. It just looks like GL compute shaders. There are lots of hard parts in OpenCL that have historically prevented us from getting conformance. OpenCL 3.0 means that most of this is optional again because we just declared Kronos bankruptcy and all the features. So things get easy again. So OpenCL 3.0 is far less featureful than 2.1. That is a natural progression. Don't even worry about it. So that's great. There are some hard parts in the shaders that we now have to support, things like 8-bit and VEX16, but NUR has lowering passes for literally everything, so you just get to support what your hardware does when you already had from OpenGL. So my question is to the maintainers of people of GLES 3.1 class drivers, so Gallium drivers with compute shaders, where the hell is your OpenCL driver? Thank you.
Hi, I'm Magali. In this lightning talk, I'll talk about unit test coverage from KUnit tests in the DRM system, which in this case encompasses not only the DRM subsystem, but also the work we developed in AMD's display driver, which we talked about 2 days ago. So this talk will go over how test coverage can be of great help to identify areas that need more test cases, and therefore avoid less and less regressions. So a little bit of context. How did KUnit end up in the DRM subsystem in the first place? Going back in time a little bit, there was a task in the DRM subsystem that consisted of converting the self-tests to KUnit, and last year there was a hackathon that involved 2 major Brazilian universities, and the students from this hackathon converted the self-tests. And after a few months, my colleague, Maíra Canal, finally did the final tweaks and sent those tests to the mailing lists, and they are now available in the DRM tree, and they were just pulled to the mainline yesterday. So as of now, the DRM subsystem has not only those tests that were converted to that were self-tests, but also new tests that are being developed by the community. And okay, so tests and new tests. So to generate the test coverage using KUnit, we have to use the KUnit script, the Python script that is under the Linux repository, but there are actually 2 limitations. We have to use a GCC version that is older than 7, and the only architecture that this script supports is UML, so we're a bummer. So this is the command to generate the test coverage, and as you can see, the only difference between running this command and the command to just run the tests is that we have to enable more config entries. Then we can use lcov and genHTML to generate the HTML pages to see the test coverages. And now on to seeing the result of all of this. These are the results from the test coverage results from the DRM helper functions. So those self-tests and also the new tests. As you can see, it's not very covered, so there's room for improvement. And so take, for instance, this function. Using the test coverage tool, we can see, we can have more ideas of test cases that we can write. And this is a tool, a task that can be done both by beginners, since it is quite simple, and also by experienced developers who wish to strengthen the DRM subsystem. And this is the result that we achieved in the Google Summer of Code project in the AMD's display driver. Also not very high, but this is what we achieved. And we mainly focus on DMUB, these file on the first square rectangle, and then the DML folder. And in summary, test coverage is a metric that can help us build test cases, and we have to keep in mind that we just don't want any sort of high coverage just for having high coverage. We have also to take into account the quality of tests. So that is it.
Zink on Rusticl or the other way around. So let's see. Oh, no, that's better. So here it is. So that's running on Env, the Intel Vulkan driver, and seems to work now. So it probably also works on Redry. It's only using the physical buffer address extension on top of pretty much what Zink needs. There's some wrong rendering in the middle, but don't worry about that. We'll figure it out. And yeah, that's essentially it. In case you're interested to make it run as well, you can probably just try it out. I have a Rusticl / Zink branch with a couple of hacky patches and a pile of stuff. Jason and Mike helped a lot out with this, so big thanks to them. Yep, that's it.
So hello and welcome. This is the closing session of XDC, and we weren't alone this year. So there were two conferences joining us, WineConf and FOSXR. Both of them were streamed. And if you haven't attended the talks from the other conferences, you can just watch them on YouTube. So right now, this is like a huge VOD that you can watch and scroll. Hopefully, we will have community contributions soon with timestamps. And sometime over the next week or two, I'll try to chop it up and upload these as separate talks. So as a reminder, upload your slides, go to your submission in Indico, click on that crayon icon, and make sure that your presentation materials are up there. So I would like to have a few shout outs. So first off is the University of St. Thomas. So this is the place we are in. So they provided us with those facilities and all those rooms for the conference. Obviously, we had to pay for it, but not much. So thank you. The other thing is the WineConf. So the whole idea of getting us together was that we kind of working on common goals, and a lot of the development of the 3D graphics stack on Linux is kind of driven by gaming, and Wine is enabling that gaming to happen. So we're intertwined in that way. We have some old-timer Mesa contributors in the Wine community. I came from like kernel side and IGT staff development to Wine as well. And yeah, we're just one big family, so why not meet up together? Although they also made quite a few sacrifices, because usually WineConf is more like a bar camp and conference where there's no schedule, not much going on, so they have adapted to the way X.Org is doing things.
It's bar camp because we just go straight to the bar.
Yeah, it's a bar camp because we go straight to the bar. So you've seen me and you've seen Jeremy, who are like the faces of the organizers, but there were a lot of more people who helped make this thing happen behind the scenes. So there's James, who helped us find the location and do a lot of planning for it. There's Jeremy Newman, who helped setting the whole thing up, like all the cables you see here, sourcing all the equipment for streaming. That was his work. So
Anybody who's plugged in owes Newman, just saying.
Exactly, but go buy him a beer. There's Tressa, who also helped a lot with planning things, finding places, and just like making this event awesome. And there's Jana, who helped a lot with budgets and marketing and graphics. There's also a few people who helped handling streaming. So those are not people who are part of the organizers. Those were people who were just planning to attend and stepped up and helped running the show for you. So for Wine, that was Henri, who ran basically the whole conference by himself. For XDC, we had Andre, who is right now like sitting in my spot and helping whenever I had some other things to do and had to run around for the other conferences. And there's also Martin, my longtime friend, who's sitting over there and also helped quite a bit. For FOSXR, this is the FOSXR organizer, who also just was provided with the streaming setup, few instructions, and like, you're on your own now. And he pulled it off. So there were a few mishaps through the whole event. The first one is misattributing of certain talk to Bas. I'm looking forward to seeing presentation titles like that from Bas next year, though. The next one was like a peek behind the curtains, because I failed to switch to the correct scene at one point, and you could see how we do panning in our software. So you've seen the stuff behind the scenes. And the other one was the fake boxing match with like some high schoolers came in with referees, started punching each other. One fell to the ground, started screaming something about 911, and then we just called security and they kicked them out. So that was quite good. They were filming that for TikTok or YouTube or something. I don't know. There was also one streaming machine that needed a reboot, because that was FOSXR room. Whenever you plugged in external HDMI to it, nothing happened. It was just a black display. So luckily, you are all not on the hook for that one, because that was MacBook running macOS. So it wasn't our fault. And that's all I have to say.
So I think the most important thing, and the person who has very clearly worked the hardest over these past 23 days, is our friend Arik Healer. Thank you for all your work. And then we do have the space for a while, so you are welcome to stay and have whatever left of the cookies and the water. So don't, I was joking next door that I was kicking you out, but I'm not actually kicking you out. You're welcome to linger and network and communicate. And thank you all so much for coming, and thank you for allowing us to have you. I think that's all. Cheers.